Usually when we look at the universe, we imagine planets tracing perfect circles around the sun, comets streaking across the darkness, and countless stars scattered like sparks across the night sky. But what if the real secrets of our cosmic neighbourhood aren't just spread out around us, but also towering above and plunging far below? High above, titanic bursts of gamma rays blaze toward the galactic north. Deep below, unseen rivers of gravity twist and pull, shaping our path through the stars. Together they reveal that our solar system isn't a flat stage, it's a vast, layered theatre with heights and depths still waiting to be uncovered. Before we begin, drop a comment below and let us know where you're watching from and what time it is for you right now. Now, settle in for a journey through the universe that will change the way you see it forever. When most people imagine looking up at the universe, they picture the sweeping arc of the Milky Way, its bright stars scattered like glowing grains of sand across the night sky. Astronomers often speak of the galactic North Pole, a direction that points outward from the plane of our galaxy and offers a clear view of distant space. The North Pole has historically attracted a great deal of attention because of its clarity and the wealth of ancient galaxies that can be seen in that direction. But the universe is never one-sided. For every north, there is a south, and just as the galactic North Pole gives us a window into the cosmos, its counterpart, the galactic South Pole, reveals a view no less valuable, no less extraordinary, and no less profound. To look toward the galactic South Pole is to open another cosmic window, one that helps us balance our picture of the universe and understand the Milky Way from both above and below. The galactic South Pole is not an abstract concept but a precise point in the sky. It lies in a constellation known as Sculptor, a faint grouping of stars first catalogued by the French astronomer Nicolas Louis de Lacaille in the 18th century. This constellation is not especially bright or obvious, but hidden within its borders is a doorway to the farthest reaches of the universe. To understand its position, imagine the Milky Way as a great spinning disk, something like an enormous celestial pinwheel. The disk is flat with spiral arms winding outward, filled with billions of stars, clouds of gas and streams of dust. From this disk rise two poles, the north and the south. The galactic South Pole is located exactly 90 degrees beneath the plane of this disk, standing as the precise opposite of the galactic North Pole in the system astronomers use to map our galaxy. Although the North Pole often takes the spotlight in research papers, conferences and headlines, the South Pole is equally crucial. Without it, astronomers would see only one side of the galaxy's symmetry. By comparing the North and the South, they can test whether the Milky Way is balanced, whether its halo of stars and dark matter is truly spherical, or whether one side has been shaped differently by history and time. From Earth, the galactic South Pole is most clearly visible in the skies of the Southern Hemisphere. People in places such as South America, Africa and Australia have the best vantage point to study it. For those living in the Northern Hemisphere, this pole never rises above the horizon, making it a treasure hidden from half of humanity's eyes. Like its northern twin, this southern region of the sky is unusually quiet. In astronomy, quiet means that it is not crowded with nearby stars, glowing gas, or the dark streaks of interstellar dust that so often block our view. Instead, the centre of this polar region is remarkably empty. And in astronomy, emptiness is a blessing. A quiet field gives us a wide-open window into the deep universe, allowing us to see beyond the Milky Way and into the greater structures that make up the cosmos. Clusters of galaxies, vast filaments of matter, and the immense dark voids in between. The galactic South Pole has long been a favoured hunting ground for astronomers who want to map the universe in 3 dimensions. One of the most famous of these projects was the 2-degree field galaxy redshift survey, often abbreviated as 2D-DFGRS. This ambitious effort, carried out in the late 20th and early 21st centuries, measured the distances to more than 200,000 galaxies. Why was the galactic South Pole chosen for such a monumental project? The answer is simple: clarity. Because this region of the sky has very little dust or gas in the way, it suffers from extremely low extinction. In other words, its view is not blurred or dimmed by material within our galaxy. This clarity makes it one of the best cross-sections of the universe available to astronomers. By studying the galaxies beyond the South Pole, scientists were able to create some of the first large-scale maps of the universe's cosmic web. These maps reveal that galaxies are not scattered randomly through space. Instead, they are strung together in vast chains and sheets, with enormous voids in between, an arrangement often called the cosmic web. The galactic South Pole was one of the first windows through which humanity saw this grand architecture. Although looking outward through the South Pole shows us the universe beyond, it also reveals secrets about our own galaxy. By tracing how stars and gas thin out as we move away from the Milky Way's central disk, astronomers can measure the shape of the galaxy's halo, the vast, faint sphere of stars and invisible dark matter that surrounds the disk. When data from the North and South Poles are compared, astronomers gain an especially powerful tool. If the Milky Way were perfectly symmetrical, the two poles would look identical, but research suggests that this is not the case. The southern view, in particular, shows hints of asymmetry. These irregularities may be the lingering scars of ancient galactic collisions. Over billions of years, the Milky Way has not grown in isolation. Instead, it has pulled in and absorbed smaller galaxies, a process sometimes called cosmic cannibalism. The stars and dark matter from these captured systems leave behind faint streams, ripples and clumps that are easier to detect when viewed from the clear vantage of the South Pole. In this way, the galactic South Pole becomes a kind of historical record, preserving evidence of the Milky Way's violent growth. The galactic South Pole is not only a window into history, it is also a practical tool for modern astronomy. Many space observatories use it as a calibration field. Calibration means checking and fine-tuning the instruments to make sure their measurements are accurate. Telescopes such as Galactic, which observed ultraviolet light, Spitzer, which studied the infrared universe, Chandra, which focused on X-rays, and Planck, which mapped the cosmic microwave background, all relied on the polar regions of the galaxy for this purpose. Because these areas are relatively free of foreground clutter, they are perfect places to test instruments against faint and distant signals. For example, the Planck spacecraft used the galactic poles to refine its measurements of the cosmic microwave background, the faint afterglow left over from the Big Bang nearly 14 billion years ago. Without the clear skies of the galactic South Pole, such delicate observations would have been nearly impossible. The galactic South Pole is also home to two of the Milky Way's closest companions, the Sculptor Dwarf galaxy and the Fornax Dwarf galaxy. These small, faint galaxies orbit our own much larger system, and though they contain far fewer stars than the Milky Way, they are scientifically priceless. Because these dwarf galaxies are dominated by dark matter, studying them helps astronomers refine their models of how galaxies form and grow. By tracking the motion of stars within Sculptor and Fornax, researchers can measure how invisible dark matter shapes their gravity. These measurements, in turn, reveal clues about how the Milky Way itself has been building its mass over billions of years. In a sense, Sculptor and Fornax are like living fossils, small ancient systems that preserve the conditions of the early universe. Their presence near the galactic South Pole makes this region even more important. The South Pole also overlaps with an area known as the South Galactic Cap, a high-latitude region that has become a favourite target for deep sky surveys. Just as the North Galactic Cap has revealed immense filaments of galaxies and the vast emptiness of cosmic voids, the Southern Cap offers a complementary view. Only by combining surveys from both the North and the South can astronomers build a complete three-dimensional map of the universe. If one half were missing, the picture would be unbalanced, like trying to understand Earth's geography while ignoring an entire hemisphere. The galactic South Pole ensures that our cosmic cartography is full and accurate. In recent years, a new field of astronomy has emerged, the study of gravitational waves. These are ripples in space-time itself, produced by cataclysmic events such as the collision of black holes or the merger of neutron stars. Projects such as LIGO in the United States and Virgo in Europe have already detected dozens of such waves, confirming predictions first made by Albert Einstein more than 100 years ago. In the coming decades, new observatories, including a space-based mission called LISA, will expand this work. For gravitational wave astronomy, the polar regions of the galaxy are invaluable. Because they are visible for long stretches of time, they allow continuous monitoring of potential events. The galactic South Pole, therefore, is not just a window to light, It is also a listening post for the deep rumble of the universe. Another mystery that the South Pole helps to unravel is the Milky Way's magnetic field. Like invisible lines of force, these magnetic fields thread through the galaxy, shaping the motion of charged particles, guiding cosmic rays, and influencing the flow of interstellar plasma. While most of these fields follow the spiral arms of the galaxy, some curve upward and downward into the halo. By observing them from the vantage of the South Pole, astronomers gain a vertical perspective, as though stepping back to see the entire structure in 3 dimensions. Mapping these magnetic lines is essential for another reason. They create foreground noise that can interfere with the search for faint cosmic signals. By carefully studying the magnetic fields at the galactic South Pole, scientists can build cleaner models that help separate the whisper of the early universe from the hum of our galaxy. In the language of science, the galactic South Pole is also known as a control field. When researchers study the universe, they need reference regions, patches of sky that are relatively empty and quiet, against which they can compare their more crowded observations. The South Pole provides exactly such a region. By using it as a baseline, astronomers can test their models of dark matter density, refine measurements of baryon acoustic oscillations, the faint ripples in the distribution of galaxies left over from the early universe, and confirm the reality of faint distant galaxy clusters. Without such a control field, many cosmological results would remain uncertain. It is true that the galactic North Pole often receives more attention in news headlines, especially when deep field images or cosmic microwave background studies are released. But the South Pole is no less important. Together, the 2 poles offer balance, symmetry, and perspective. The South Pole is a mirror to the North. It shows us whether our galaxy is truly even or slightly skewed. It provides a second calibration point for our instruments, ensuring that our cosmic measurements are accurate. It gives us access to quiet regions of space, where the universe can be studied in its purest form. Perhaps most importantly, it reminds us that no single viewpoint is enough. To truly understand the Milky Way, the cosmic web, and the grand structure of the universe, we must look in both directions, north and south, above and below, outward and inward. Try to picture yourself rising high above the solar system, far beyond the Earth, the Sun, and the planets. From this impossible height, you look down, not from any mountain or spacecraft, but from a place that floats outside the familiar bonds of home. You're no longer tied to the spinning Earth or to its curved horizon. You're out in the silence of space, where directions such as up and down lose their usual meaning. Here in space, there is no floor, no ceiling, no walls, only endless blackness scattered with stars. Yet astronomers, the people who devote their lives to understanding the universe, cannot afford to wander without guidance. They need a fixed direction, a stable marker, something that never wavers no matter where they look or how far they travel. On Earth, we have the North Pole, the South Pole, and the lines of latitude and longitude that help sailors and pilots find their way. But what about in space? That is where the idea of the galactic North Pole comes in. The galactic North Pole is not a glowing star, nor is it a bright beacon shining above the Milky Way. It is instead a point, an invisible, purely geometric direction in the sky that scientists use as a kind of cosmic compass. Though it cannot be seen with the naked eye, its importance is extraordinary. By pointing toward it, astronomers decide which way is above the flat disk of our galaxy. To imagine this more clearly, think of the Milky Way as an enormous disk, something like a record or a DVD, only millions of times larger than our entire solar system. It is wide but very thin, with billions of stars, clouds of gas and streaks of dark dust spread across its surface. Now, if you were to stick a pin straight through the middle of that disk at a perfect right angle, the pin would poke out on both sides. One end would point upward. That is the galactic North Pole. The other end would point downward. That is the galactic South Pole. The galactic North Pole lies in the sky in the direction of a faint constellation known as Coma Berenices, the Hare of Berenice. It is not a famous constellation like Orion or Leo, though Leo, the great lion, rests nearby. Coma Berenices is made of soft, dim stars that look almost like a cloudy patch. Yet in that quiet patch of sky, astronomers have anchored one of the most important reference points in all of space. Unlike Earth's North Pole, which shifts over time because of the planet's wobble, The galactic North Pole is fixed in a way that feels eternal. The Earth may tilt and lean, but the galaxy's frame remains steady. It is, in short, the ultimate up of the Milky Way. One might ask, why is this so important? Why does anyone care which way is up when there is no gravity in space to define it? The answer is that the universe is not a random sprinkle of stars. It is highly structured. Galaxies spin, stars form in vast clusters, black holes pull on their surroundings, and invisible rivers of gravity shape the paths of galaxies themselves. To measure any of this, astronomers need a fixed frame of reference. When scientists study the tilt of galaxies, the movement of our own solar system, or mysterious phenomena such as the Great Attractor, an enormous gravitational anomaly pulling entire galaxies toward it, they need to say, we are moving this way, tilted at this angle, pointing in this direction. Without a standard point like the galactic North Pole, every measurement would be uncertain. Just as a pilot uses pitch, roll, and yaw to describe the orientation of an airplane, astronomers use three-dimensional directions to describe the orientation of the solar system. The galactic North Pole is the anchor of that system. To find this special point, astronomers invented what is called the galactic coordinate system. It works much like Earth's latitude and longitude. On Earth, the equator divides the globe into north and south, and from there we measure degrees of latitude. Longitude lines, running from pole to pole, let us measure east and west. In the galaxy, the disk of the Milky Way plays the role of the equator. The galactic North Pole is defined as the point lying at 0 degrees longitude and plus 90 degrees latitude in this system. Its mirror opposite, the galactic South Pole, lies at minus 90 degrees. When astronomers point their telescopes at this direction, something remarkable happens. Their view clears. The dense clutter of stars, gas and dust that fills the main disk of the Milky Way falls away. Instead of peering through a fog of galactic material, the telescopes gaze through a much cleaner window of space. This window makes the galactic North Pole one of the best places in the entire sky for deep observations. Through it, astronomers have spotted some of the most distant galaxies ever known. Light that has travelled for billions of years streams through this opening, reaching our instruments without being swallowed by the dust of our own galaxy. By observing through this direction, scientists have also mapped the halo of the Milky Way, a vast, ghostly bubble of dark matter, thin gas, and scattered ancient stars that stretches far beyond the glowing spiral arms. The halo is invisible to ordinary sight, yet it contains much of the galaxy's hidden mass. Without the clear path offered by the galactic North Pole, charting this faint structure would have been nearly impossible. But the usefulness of this cosmic compass does not end there. The galactic North Pole also provides one of the best vantage points for studying the cosmic microwave background radiation, the faint glow left over from the birth of the universe itself. This radiation, which fills every corner of space, is the cooling afterglow of the Big Bang, the event that began the universe nearly 14 billion years ago. To study this delicate signal, scientists need quiet regions of sky, places not filled with the noisy radiation of stars, dust and gas. The Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck Observatory both turned their eyes toward the galactic North Pole for exactly this reason. Looking there is like peering back across nearly the entire history of the cosmos, to a time when the first atoms were forming and light itself was just beginning to travel freely. Even newer branches of science, such as the study of gravitational waves, rely on knowing the orientation of the galaxy. Gravitational waves are ripples in space-time created when enormous objects, like black holes or neutron stars, crash into one another. Detectors on Earth, such as LIGO and Virgo, record the faint tremors from these cataclysmic events. But to make sense of the signals, astronomers must know exactly where they are within the galactic frame. These violent events are not scattered randomly. They cluster around regions of great mass, following the invisible skeleton of cosmic structure. By mapping their positions relative to the galactic north and south poles, patterns emerge that would otherwise remain hidden. Meanwhile, our solar system itself is far from fixed. The Sun, along with its planets and comets, drifts in a slow, stately orbit around the centre of the Milky Way. This journey takes roughly 230 million years to complete. In other words, since the time of the dinosaurs, the Sun has circled the galaxy less than 3 times. As the solar system moves, its angle to the galactic North Pole changes. The journey is part of a graceful, endless dance, a slow circling in the sea of stars. Knowing where the galactic North Pole is today helps scientists trace where we were long ago and predict where we will be millions of years from now. It is almost poetic that something so invisible, something that no eye can see without mathematics and careful definition, can serve as such a powerful anchor. The galactic North Pole does not shine, does not glow, and yet without it we would be lost. It is the silent compass needle of the galaxy, guiding our measurements, our observations, and even our imagination. This naturally leads to a deeper question. What truly lies above the North Pole of the Sun? If we were to rise straight upward, past the fiery crown of the Sun, past the circling orbits of the planets, and past the far-off cloud of comets that marks the edge of our solar system, what would we find? The answer is not a wall, nor an edge, nor a ceiling. We would pass into the immense open dark. We would pass distant galaxies, glowing quasars, and webs of matter stretching across billions of light years. Each layer would carry us farther back in time, farther into the unfolding story of the universe. And through it all, the galactic North Pole would remain our arrow, pointing the way into the greatest mysteries of all. Far above the blazing surface of our Sun, past the boiling storms that churn across its face, there lies a region that is both mysterious and powerful, the solar polar region. This is not an empty, quiet stretch of space. It is a place alive with invisible forces, where the Sun's magnetic fields bend, twist and stretch like giant ropes under tension. It is also where rivers of blazing hot plasma, streams of charged gas so hot that atoms themselves have been torn apart, are constantly shifting and flowing outward. If you look toward the equator of the Sun, the story looks different. There, dark patches known as sunspots appear and fade like bruises on the solar surface, and violent explosions called solar flares burst outward with tremendous force. But the poles of the Sun are quieter in comparison. Quieter, yes, but not silent, and certainly not lifeless. The poles are not a place of inactivity. They are like hidden engines, quietly but powerfully shaping the environment of the entire solar system. What happens above the poles does not stay there. It stretches outward and influences the space that every planet, every comet, and even our Earth must live within. The Sun is not steady or unchanging. It has a natural rhythm, a heartbeat of sorts, called the solar cycle. This cycle repeats roughly every 11 years. During this time, the Sun's magnetic field becomes tangled and chaotic, then slowly reorganizes itself, flipping its north and south poles in the process. One of the calmest moments in this cycle is known as the solar minimum. This is the quiet phase, when sunspots nearly vanish and the Sun's magnetic field smooths itself out. At the poles, during solar minimum, the field lines straighten and stretch outward into space like tightly drawn arrows. From these poles, powerful but invisible rivers of solar wind, streams of high-speed particles shoot outward across the solar system. These particles are not drifting aimlessly. They are busy workers in the construction of something enormous, the heliospheric current sheet. This is an unimaginably large and warped spiral of magnetic influence that spreads out from the Sun like a giant rotating skirt, wrapping around every planet and every piece of space within the solar system. It is one of the greatest invisible structures in existence, and it begins, in large part, with the winds flowing outward from the solar poles. In the year 1990, humanity took its first bold step toward exploring this unseen world. That year, the Ulysses spacecraft was launched. Ulysses was unique because it was designed not to circle around the Sun's equator, like most spacecraft naturally would, but to soar high over its poles. It was the first mission to view the Sun from this extraordinary angle. Throughout the 1990s and into the early 2000s, Ulysses completed several journeys above both the north and south poles of the Sun. What it discovered was groundbreaking. The winds above the poles, it revealed, were not the same as those near the equator. At the poles, the solar wind blew faster, was thinner, and far more steady. In contrast, the winds near the Sun's equator were thicker, denser, and more chaotic, changing speed and direction in unpredictable ways. This fast polar wind is not just an interesting curiosity, it is one of the key forces that sculpts the heliosphere, the gigantic bubble that surrounds our entire solar system. The heliosphere is not just empty space, it is a shield. It acts like a protective barrier that pushes back the most dangerous cosmic rays coming from deep in the galaxy. Without it, Earth and the other planets would be exposed to far higher doses of deadly radiation. The heliosphere is, in a very real sense, a life-preserving cocoon, and the steady winds of the poles are part of what gives it its shape. You can think of the space above the Sun's North Pole as a kind of cosmic gateway. It is the starting line from which streams of energy, particles and magnetic waves launch outward into the galaxy. If you followed those streams outward, far past the orbit of Neptune and Pluto, you would eventually reach the edge of the heliosphere, the place where the Sun's influence finally fades and the galaxy takes over. At this outer edge, the solar wind particles are fewer and weaker. The Sun's magnetic field stretches into long, thin strands that eventually begin to tangle with the great magnetic fields drifting between the stars. This is where the Sun's power surrenders to the greater forces of the Milky Way galaxy. In the year 2012, a spacecraft named Voyager 1 reached this frontier. Launched back in the late 1970s, Voyager 1 had travelled for decades before finally crossing the invisible boundary of the heliosphere. It did so near the Sun's northern edge, which means that, in a galactic sense, it passed above the Sun's North Pole. What lies beyond this border? The local interstellar medium, a thin sea of gas, dust and high-energy cosmic rays flowing between the stars. Right now, our Sun is drifting through a patchy part of this medium known as the local interstellar cloud. This cloud is slightly warmer and denser than the surrounding space, and it presses against the heliosphere, squeezing it on one side and stretching it on another, like the wind pressing against a balloon. Because the Sun is not standing still but racing through the galaxy at thousands of miles per hour, the heliosphere is not a perfect round bubble. Instead, it forms something more like a teardrop, with a blunt nose facing forward in the direction of the Sun's travel. Interestingly, this nose is not perfectly centred. It tilts slightly upward, toward the region above the solar system's midplane and close to the Sun's North Pole. This tilt means that many of the strange effects, particles and waves that deep space probes encounter, come from above, not from the flat plane of the planet's orbits. In a sense, the North Pole of the Sun is not just pointing upward, it is pointing forward, toward the future, into the direction the Sun itself is travelling through the galaxy. If you could rise even higher, leaving the heliosphere altogether, the view above the Sun's North Pole would open into the wider galaxy. This direction offers one of the clearest windows into deep space. Unlike other directions where interstellar dust blocks and scatters light, the path above the North Pole is relatively clean and clear. This gives astronomers a nearly unobstructed view into the depths of the cosmos. Powerful instruments such as the Chandra X-ray Observatory and the Planck spacecraft have taken advantage of this direction. By peering along this window, they have studied distant galaxies, measured faint radiation left over from the birth of the universe, and tracked mysterious high-energy X-ray sources. The North Pole of the Sun, in other words, points directly into some of the clearest lines of sight we have into the grand history of the cosmos. Even cosmic rays, the ghostly particles that zip across the universe and constantly rain down on Earth, show unusual behaviour in this direction. Studies have revealed that slightly more of them seem to arrive from the galactic north than from other directions. This suggests that the region above the Sun is not just empty sky, but may be shaped by hidden structures and energetic events we do not yet fully understand. In many ways, the space above the Sun's North Pole is not fully the Sun's domain, but it is not fully the galaxy's either. It is a borderland, a transition zone where the two powers overlap. On one side, the Sun's influence still flows outward. On the other, the vast forces of the Milky Way press inward. Together they create a frontier, a cosmic meeting ground where two great realms, the solar and the galactic, touch and intermingle. It is in this frontier that some of humanity's most daring spacecraft have already travelled. The twin Voyager probes went this way, and more may follow. NASA is currently studying the idea of an interstellar probe, a spacecraft designed specifically to leave the heliosphere and explore the interstellar medium directly. If built, it too would most likely travel northward, upward, and outward, just as Voyager 1 did. This path above the Sun's North Pole, then, is not just an abstract idea for scientists. It is a direction that humanity itself has already begun to follow. From the first discoveries of Ulysses to the long journey of Voyager 1, and perhaps soon to the future interstellar probe, we have been reaching outward through this northern corridor. Every step takes us farther from the cradle of the Sun and closer to the ocean of stars beyond. To travel northward above the Sun is to leave behind the familiar rhythms of our solar system and enter a realm shaped by the galaxy itself. It is a journey from the known into the unknown, from the warm glow of our star into the deep, cold mysteries of interstellar space. High above us, hidden within the hazy glow of the Milky Way, lies a structure so mysterious that most people on Earth have never even heard its name. Yet astronomers have been carefully studying it for many decades, searching for answers to questions that remain unsolved to this very day. This strange formation is called the North Galactic Spur, and to the naked eye it appears like a faint ghost stretching across the northern heavens, almost as if an enormous dusty bridge had been hung across the stars. At first glance, the spur is easy to overlook. Unlike the bright, dazzling band of the Milky Way that shines with the light of billions of stars, this feature is tricky to spot. In visible light, it is hidden and obscured by thick clouds of gas and dust, which block much of its natural glow. But when astronomers turn their special instruments toward it, radio telescopes that can detect invisible radio waves, detectors that sense microwaves, and even X-ray instruments that capture the most energetic forms of light, the North Galactic Spur suddenly reveals itself. Through these cosmic new eyes, it becomes one of the most striking and powerful features in the entire sky. The spur is not a small or local cloud of dust. It is enormous. In maps made with radio waves, it appears as a long, curving filament shaped almost like a giant arc. This arc rises high above the flat plane of the Milky Way galaxy and then curves back downward again, forming a sweeping loop. The structure seems to begin close to the very heart of the galaxy, not far from the galactic centre itself, and then it extends outward across a vast portion of the northern sky. To the imagination, it looks almost like the mark of a cosmic paintbrush. Picture a giant hand sweeping across the heavens with a single brushstroke, leaving behind a glowing trail. That trail in many ways resembles the shape of the North Galactic Spur. Its sheer size is difficult to grasp. On the sky, it stretches across dozens of degrees, covering a region far larger than the Moon, the Sun, or even many familiar constellations. Despite decades of study, astronomers are still debating what exactly the spur is. Several competing theories exist, each one fascinating in its own right. One popular idea suggests that the spur is part of something called a superbubble. A superbubble is a gigantic shell of gas and dust, pushed outward by the combined explosions of many massive stars. When giant stars reach the end of their lives, they do not fade quietly. Instead, they explode as supernovae with unimaginable power, releasing more energy in a single moment than our Sun will produce over its entire lifetime. If several of these colossal stars exploded in the same general region of the galaxy, their shock waves could combine, sweeping gas and dust outward into a gigantic arc. Over time, this would leave behind a loop-like scar across the heavens, the very scar that we now see as the North Galactic Spur. If this explanation is correct, then the spur is more than just a faint arc of dust. It is a cosmic memory, a visible reminder of the titanic violence of ancient stars that perished millions of years ago. Other scientists argue for a very different explanation, one that places the spur much closer to home. According to this view, the spur may not be part of a massive galactic shell at all. Instead, it could be a wall belonging to something called the local bubble. The local bubble is the region of space that our solar system is currently drifting through. It is filled with very hot, very thin gas, which is electrically charged and spread out over hundreds of light years. This bubble too was likely carved out by a chain of nearby supernova explosions. But these explosions happened relatively recently, perhaps only a few million years ago, and not far from our Sun. If this theory is true, then the North Galactic Spur is not a vast galactic structure spanning thousands of light years. Instead, it is more like a nearby scar, a local wall of gas and dust left behind by violent events that took place in our cosmic neighbourhood not too long ago. There is also a third possibility, which combines the first two. Some astronomers believe that the spur might actually be both a local structure and a galactic-scale feature layered on top of one another. If that is the case, then when astronomers point their telescopes at the spur, they are looking through several overlapping layers of gas and dust. Each layer could be located at a different distance, moving at a different speed, and shaped by different events. This overlap makes the problem extremely complicated. It is a bit like standing on the ground and trying to sketch the shape of a mountain range while thick clouds drift across the view. The clouds might hide some peaks, exaggerate others, and even create illusions. Untangling the spur's true shape and origin is just as tricky. The North Galactic Spur is not simply a curiosity for astronomers to puzzle over. It also plays a very important role in some of the most sensitive scientific experiments ever conducted. One of the greatest achievements of modern science was the discovery and study of the cosmic microwave background, or CMB. This faint glow is the afterlight of the Big Bang itself, the leftover radiation from the birth of the universe nearly 14 billion years ago. In order to study this faint signal, scientists launched satellites like WMAP, Wilkinson Microwave Anisotropy Probe, and later the Planck mission. These instruments measured the CMB with incredible precision. But there was one major challenge. Our own galaxy produces microwave radiation as well, which can contaminate the signal. The North Galactic Spur was one of the biggest sources of this contamination. Because it shines strongly in polarized radiation, it created a kind of foreground noise that scientists had to carefully subtract from their data. Without accounting for the spur, the delicate patterns of the CMB, which reveal information about the early universe, could have been completely misinterpreted. At one time, some researchers even thought that signals from the spur might be hints of something much stranger: dark matter annihilation near the galactic center. Dark matter is one of the biggest mysteries in science. It does not emit or absorb light, yet its gravity shapes galaxies and clusters of galaxies. When astronomers detected unusual radiation near the center of the Milky Way, some believed it might be the result of dark matter particles colliding and destroying each other. But later studies revealed that much of this strange radiation was not exotic at all. It was caused by ordinary structures like the spur. This was an important lesson. It showed just how critical it is to understand our own galactic environment. Misinterpreting something nearby can lead to false conclusions about the universe itself. The spur also provides scientists with a rare opportunity: the chance to study magnetic fields on the scale of the galaxy. Normally, magnetic fields are invisible, but inside the spur, tiny dust grains align themselves with the Milky Way's magnetic field lines. This alignment causes the dust to emit polarized light waves that are oriented in specific directions. By mapping this polarized light, astronomers can trace the otherwise invisible structure of the magnetic fields that weave through the galaxy. This is an extraordinarily difficult thing to study, and the spur serves as a natural laboratory for it. In this sense, the spur is not just a cosmic curiosity, but a crucial scientific tool. And yet, even with all this knowledge, the North Galactic Spur remains a mystery. It does not behave like a simple arc. It does not fit neatly into any current model of the Milky Way structure. At times, it seems like a trick of perspective, a strangely shaped cloud of dust that just happens to look like a sweeping arc when viewed from Earth. At other times, it seems like something vast and powerful, a structure whose true shape we're only beginning to glimpse. The truth may be stranger than any of the current theories. The universe, after all, often surprises us. The future holds hope for solving this riddle. New missions with advanced technology will soon provide astronomers with three-dimensional maps of the sky at an unprecedented level of detail. One such mission is Sphere X, the spectrophotometer for the history of the universe, epoch of Ryanization, and ICES Explorer. With instruments like these, scientists may finally be able to measure the true distance of the spur, trace its actual shape, and uncover its origins. Perhaps they will find that it is a nearby wall of the local bubble, or perhaps they will discover that it is indeed the scar of ancient supernova from the heart of the galaxy. Or maybe, as often happens in science, they will find something entirely unexpected, something no one has yet imagined. Until that day arrives, the North Galactic Spur remains what it has always been, a dusty bridge suspended above our heads, stretching across the northern sky. It carries with it mystery, history, and the echoes of events that shook our galaxy long before humans ever looked upward to wonder about the stars. When you look up into the night sky and see the glowing band of the Milky Way, imagine that faint ghostly arc running across it. Think of the massive stars that may have exploded to create it, or the cosmic bubbles of gas that may surround us. Think of the magnetic fields, the radiation, and the secrets hidden in its light. High above our heads, far beyond the reach of the mountains, airplanes, and even satellites, there is a hidden but immensely powerful point in the northern sky. It is called the North Celestial Pole. You cannot touch it, and you cannot see it directly, for it is not a star or a planet. It is simply a point, a direction in space. Yet its importance is so great that for thousands of years it has guided sailors across dangerous seas, led explorers across deserts and forests, and helped astronomers unlock the secrets of the heavens. It is one of those quiet mysteries of the universe, invisible, untouchable, but shaping the way humans have travelled, built, and dreamed for countless generations. To understand the North Celestial Pole, imagine the Earth spinning like a great top. Our planet rotates around an invisible line called its axis of rotation. This axis runs through the Earth from the geographical North Pole to the geographical South Pole. If you extended that axis far, far out into space, the point where it touched the northern sky would be the North Celestial Pole. From our point of view on Earth, this pole looks like the exact centre of the heavens, the very spot around which every star of the northern sky appears to turn each night. When we watch the stars rising and setting, what we are really seeing is the effect of our planet's constant spin. The stars seem to move in great circles, but the North Celestial Pole stays fixed, holding everything together like the central nail in a spinning wheel. This makes it far more than a curious astronomical detail. The North Celestial Pole is the foundation stone of celestial navigation, the reference point for astronomy, and the pivot on which our understanding of the heavens rests. Marking this special spot for us is a star of great renown, Polaris, also known as the North Star. Polaris is not the brightest star in the night sky. That honour belongs to Sirius, but its position makes it one of the most important. Polaris sits almost exactly above the Earth's geographical North Pole. If you were standing at that icy tip of the planet, Polaris would shine directly overhead, right at the zenith of the sky. To travellers, this meant something extraordinary. Polaris always pointed north. No matter where you stood in the northern hemisphere, if you could find Polaris, you could find your direction. For countless sailors who crossed dangerous oceans before the invention of the compass, Polaris was a lifeline. They would keep their eyes on this steady star, steering their ships across the vast Atlantic or Pacific with the confidence that Polaris never lied. On land, explorers moving through deserts or uncharted forests looked for it too, knowing it was a natural compass set high in the heavens. Polaris earned its reputation as the anchor of the night sky because it barely shifts its position, while other stars wheel around it in circles. In long exposure photographs of the night sky, stars appear as glowing arcs or complete rings, but Polaris stands still, marking the north with calm certainty. Yet this perfect alignment is not eternal. Our planet is not a perfectly steady spinning top. It wobbles. This wobble is known as axial precession. Just like a child's top begins to trace a circle as it slows down, the Earth's axis also traces a huge, slow circle in the sky. One complete wobble takes about 26,000 years. That is longer than the entire span of recorded human history. This immense cycle slowly shifts the North Celestial Pole across the sky, changing which star serves as the North Star. About 5,000 years ago, the star Thuban in the constellation Draco was the North Star. Ancient Egyptian builders who raised the Great Pyramids of Giza may have aligned them with Thuban rather than with Polaris. Today, in our time, Polaris holds the title. About 12,000 years from now, the bright star Vega in the constellation Lyra will take Polaris's place as the guiding star of the North. This means that the honour of being the North Star is temporary. Polaris may seem unchanging to us, but in the grand rhythm of the cosmos, it is only passing through this role. This slow shift is not just of interest to astronomers. The position of the North Celestial Pole affects many areas of human activity. Astronomers align their telescopes with the pole to track stars and galaxies across the night sky. Without this reference point, it would be far harder to observe distant objects with precision. Engineers use the celestial pole as a reference to orient satellites and to calibrate the instruments of spacecraft travelling beyond Earth. Even communication antennas on the ground are often aligned using Polaris. Tiny shifts in the pole's position reveal the effects of the Sun and the Moon tugging on our planet. These measurements are used in precise timekeeping, in planning space missions, and even in long-term studies of climate. Many ancient structures, from stone circles to pyramids, were aligned to the North Star of their time. As the pole shifted, these monuments became silent witnesses to the changing sky. The pole, then, is more than an abstract idea. It is a tool of navigation, a guide for science, and a thread that ties human history to the heavens. From Earth, the North Celestial Pole acts like a great hinge on which the heavens swing. Every night, as our planet rotates, the stars appear to wheel around this fixed point. To the naked eye, this motion is subtle, but with patience, you can see it. Over the course of hours, constellations rise in the east, arc across the sky, and set in the west. The pole stays steady, unmoved, while the rest of the sky dances around it. Long exposure photographs show this beautifully. In such pictures, stars do not appear as single points of light but as long trails, curved like arcs of a circle. All of these circles share the same centre, Polaris, and the North Celestial Pole. It is the photographic proof that our world spins, night after night, always turning around that invisible pivot. The story of North is larger than just Earth. Our solar system has its own north, defined by the tilt of the Sun's equator. This does not line up perfectly with the Earth's north, because our planet's orbit is tilted compared to the Sun. On an even greater scale, our Milky Way galaxy has a north pole as well. It is located in the constellation Coma Berenices, far from Polaris. This means that up for Earth is not up for the solar system, and neither is up for the galaxy. Astronomers must juggle all these different definitions of north when mapping the stars or studying the faint afterglow of the Big Bang, the cosmic microwave background radiation. Because of these different poles, astronomers use three main coordinate systems to describe positions in the sky: equatorial coordinates, tied to the Earth's rotation and the North Celestial Pole; ecliptic coordinates, tied to the Sun's yearly path across the sky; galactic coordinates, tied to the structure of the Milky Way galaxy. The North Celestial Pole is the starting point of this great framework, anchoring one of the most important coordinate systems in astronomy. The North Celestial Pole is also a delicate measuring stick. Astronomers track its tiny movements against the background of distant stars. These measurements reveal the gravitational pull of the Moon and the Sun on our planet, the redistribution of mass within the Earth's oceans and atmosphere, and even the slow melting of ice caps. By studying the pole's position with precision, scientists can refine our calendars, improve climate models, and prepare for space missions that demand pinpoint accuracy. Because the Earth's axis slowly sweeps a circle in the heavens, the view of the universe changes across the ages. New stars rise into prominence, constellations shift, and the seasonal skies transform. What we see today is not what our ancestors saw thousands of years ago, and it will not be what our descendants see thousands of years from now. The North Celestial Pole, therefore, is not just a static marker. It is the silent hand that turns the great wheel of the heavens, reshaping human skies over millennia. When you look up at Polaris on a clear night, you are gazing directly down the Earth's axis of spin, at the pivot point of the sky. To generations of people, it has symbolized constancy, guidance, and direction. Yet its very constancy is an illusion, for the pole itself is always on the move. It is a paradox, a point that seems permanent, but is in truth part of a vast, slow and graceful motion that spans tens of thousands of years. The North Celestial Pole reminds us that even the steadiest things in the heavens are not fixed forever. They too are part of the great dance of the cosmos. When most people imagine the universe, the first picture that comes to mind is often a vast black emptiness sprinkled with countless shining stars. It looks still, silent, and lifeless. like a frozen ocean that never moves. But this picture is far from the truth. Space is not empty at all. It is alive with invisible forces, rivers of particles, and great unseen structures that shape everything around us. Among these hidden powers, one of the most mysterious and most important is the magnetic field. Magnetic fields are not something we can see with our eyes, yet they are everywhere. They guide the paths of tiny particles, influence the birth of stars, and even shield planets from dangerous cosmic radiation. Here on Earth, we live inside a magnetic cocoon created by our own planet's molten core, and without it, life as we know it would probably not exist. But Earth's magnetic shield is only one small layer of protection. Far above us, surrounding our entire solar system, there is an even greater shield, the heliosphere. The heliosphere is like a giant bubble blown into space by our sun. It is created by the solar wind, a steady, invisible stream of charged particles that the sun sends out in every direction. This wind never stops. It constantly flows outward, filling the solar system and pushing against the thin material that exists in the space between stars. Inside this protective bubble, the sun is in charge. Its winds and its magnetic fields control the environment, shaping the space through which Earth and the other planets travel. But beyond the bubble, the power of the sun fades, and something else begins to take over: the forces of the wider galaxy. At this boundary, the interstellar magnetic field makes its presence known. This magnetic field does not belong to our sun at all. Instead, it belongs to the galaxy itself, the great sea of stars, gas, dust, and energy that stretches far beyond anything our eyes can see. The edge of the heliosphere is not a sharp, solid wall like the sides of a glass jar. Instead, it is more like the blurry, shifting boundary where two oceans meet. On one side is the solar wind, pushing outward with all its strength. On the other side is the interstellar medium, the extremely thin mixture of gas, dust, and magnetic fields that fills the spaces between the stars of the Milky Way. When these two forces collide, neither side wins outright. Instead, they wrestle in a constant tug of war. The solar wind slows down, becomes disturbed, and finally halts at a border known as the heliopause. This is the true edge of the sun's influence, the place where the solar wind can no longer push back against the greater powers of the galaxy. Just beyond this invisible line, especially above the northern pole of the sun, the magnetic field of the galaxy itself begins to bend, twist, and flow through the region. It is here, in this strange frontier zone, that two invisible powers, the sun and the galaxy, weave themselves together. In the year 2012, humanity received a glimpse of this frontier unlike any before. A small spacecraft launched all the way back in the late 1970s finally reached the edge of the solar system. This spacecraft was Voyager 1, a probe built to study the outer planets, but destined to go much farther. Voyager 1 became the first human-made object to leave the heliosphere and enter interstellar space. For decades, scientists had wondered what this crossing would look like. They expected that when the spacecraft passed the heliopause, the direction of the magnetic field would change suddenly, flipping like a compass needle in reverse. But that was not what happened. Instead of an abrupt change, Voyager recorded something stranger and more beautiful. The solar magnetic field did not end at all. It bent gently, twisted, and slowly merged with the galactic magnetic field beyond. It was as though two invisible rivers had met, their currents weaving together into a tangled net of lines that folded, joined, and spiraled into one another. This discovery shocked scientists. It meant that the edge of the solar system was not a clean break, but rather a zone of blending, a kind of cosmic handshake between our sun and the galaxy. These magnetic fields above the heliosphere are not just background scenery. They play an active role in the life of our solar system. In fact, they are like both gatekeepers and highways. From the farthest reaches of the universe, powerful particles race through space. These particles, called cosmic rays, are born in violent places: exploding stars, jets of energy from black holes, and massive supernova remnants. They travel at nearly the speed of light, carrying immense energy. The magnetic fields at the edge of the heliosphere decide how many of these particles can enter our solar system. Sometimes the interstellar field blocks them, sometimes it bends them aside, and sometimes it channels them straight toward Earth and the other planets. During times when the sun is active and stormy, its magnetic shield grows stronger, making it harder for cosmic rays to get inside. But when the sun becomes quiet and calm, its shield weakens, and the galactic magnetic field pushes harder, allowing more cosmic rays to stream in. Scientists have even found that many of these particles come more easily from the direction of the galactic north, above the plane of the Milky Way. This is not just theory or guesswork. Instruments have actually seen signs of these magnetic battles. The spacecraft IBEX, which stands for Interstellar Boundary Explorer, along with the Cassini spacecraft that once orbited Saturn, have detected a strange glowing feature in the sky. They found a faint ribbon of energetic particles stretching across the heavens, like a scar etched in light. This ribbon appears to be aligned with the direction of the local interstellar magnetic field. In other words, it is a visible mark left by the invisible forces pressing against our solar bubble. This discovery was powerful evidence that the Sun and its heliosphere are not free-floating or untouched. Instead, they are being squeezed, shaped, and even wrapped by the galactic magnetic fields that surround us. Yet, despite these discoveries, the true shape of these magnetic lines remains a riddle. Scientists are still asking, are the lines neat and smooth, curving gently like the field around a simple bar magnet? Or are they tangled and twisted, knotted by ancient explosions, stirred by the spinning of the Milky Way, and churned by winds from countless stars? The answer is more than just a matter of curiosity. The way these lines are arranged has a direct impact on the future of space exploration. Magnetic fields can accelerate particles to nearly the speed of light, or they can trap them in deadly belts of radiation. They can disrupt spacecraft signals, expose astronauts to dangerous cosmic rays, and even confuse navigation systems that rely on charged particle flows. So how strong are these mysterious fields? Measurements suggest that the magnetic field just outside the heliosphere has a strength of about 36 microgauss. That is far weaker than the magnetic field on Earth, but it is still strong enough to shape the flows of particles and even influence the structure of the heliosphere itself. Some scientists believe that our solar system is currently drifting into a new part of the local interstellar cloud, a different patch of galactic material with slightly different magnetic conditions. If that is true, then in thousands of years the shape of the heliosphere could change. It might shrink or grow, offering more or less protection from deadly cosmic radiation. Over such timescales, the very environment of our planets could be reshaped by the invisible magnetic powers of the galaxy. There may even be a link between our local magnetic field and one of the Milky Way's largest and strangest features, the North Galactic Spur. This is a gigantic arc of gas, dust, and magnetic activity that rises above the disk of the galaxy like a great arching wave. Some researchers think that the interstellar magnetic field surrounding our solar system may align with this colossal structure. If so, then our solar system could be sitting inside a kind of wide magnetic corridor, a channel through which particles, dust, and radiation flow across the galaxy. If this connection is real, then our solar system's place in the galaxy is not random, but part of a much larger cosmic design. To uncover the truth, scientists are already preparing new missions. One of the most promising is the Interstellar Mapping and Acceleration Probe, or IMAP. This mission is scheduled for launch in the late 2020s. IMAP's mission will be to map out how particles gain speed at the edge of the heliosphere and how the galactic magnetic field shapes that process. Its instruments will be far more advanced than those of IBEX or Voyager. With sharper eyes and more sensitive detectors, IMAP may finally reveal the true shape and direction of the invisible lines above the Sun. For the first time, we may be able to see not just where our solar system ends, but how it fits into the grand magnetic framework of the galaxy. The more we learn, the clearer it becomes that the edge of our solar system is not a quiet boundary. It is a living, shifting frontier, a battlefield, a shield, and a gateway all at once. The heliosphere protects us, yet it is also vulnerable to the greater forces of the galaxy. The magnetic fields that twist above the Sun are not static. They bend, weave, and ripple, shaped by the life and death of stars, by the spinning of the Milky Way, and by the restless winds of space. They decide how cosmic rays reach us, how spacecraft travel, and how humanity may one day journey to the stars. Space, it turns out, is not an empty void. It is alive with power. And at the edge of the Sun's great bubble, where our star meets the galaxy, the invisible web of magnetism reminds us that we are part of a much larger cosmic story. When people look up into the night sky, most of the attention is usually drawn to the wide, bright band of the Milky Way. From Earth, it looks like a misty river of light stretched across the heavens, its countless stars merging into a shining path. Astronomers have long known that this glowing streak is actually the flat disk of our galaxy, made up of stars, clouds of gas and drifting dust. But what very few people realize is that this glittering disk is not the whole story. Far above and far below this shining spiral lies something much bigger, stranger, and harder to see. Surrounding the Milky Way on every side is a vast, ghostly sphere of matter. It is so faint and so spread out that it almost seems invisible, like a giant transparent bubble encasing the galaxy. Astronomers call this hidden structure the galactic halo. Even though our eyes cannot see it, its invisible gravity has a powerful grip on everything inside the Milky Way, binding stars, gas, and even our own solar system into a single cosmic family. As the Sun and its planets continue their endless journey around the centre of the galaxy, they do not travel through empty blackness. Instead, they drift inside the lower edge of this immense and mysterious halo, brushing against a structure whose true nature still puzzles even the brightest minds in astronomy. The galactic halo is not one single thing. It is made up of two very different parts. The first is called the stellar halo. This portion is filled with some of the most ancient stars in existence, along with great swarms of globular clusters. A globular cluster is a tight ball of hundreds of thousands, or even millions, of stars all bound together by gravity. These clusters are not new arrivals. They have been orbiting the Milky Way for billions of years. Unlike the stars in the galactic disk, which move in neat, ordered circles around the centre, the stars of the stellar halo wander like drifters. Their paths are not smooth or level, but stretched and tilted, sometimes carrying them high above the galactic plane. They seem almost restless, travelling in directions that reveal they are not native to the Milky Way. In fact, these stars and clusters act like fossils in the sky. They preserve a record of events from the galaxy's ancient past. They whisper stories of cosmic violence, telling astronomers that the Milky Way was not built all at once, but grew over time by swallowing smaller galaxies. When these tiny galaxies crashed into ours, their remains were scattered and smeared across the halo. Each lonely star wandering on a tilted path is a survivor from those long ago collisions. The second and much larger part of the halo is even more mysterious. It is made of something called dark matter. Dark matter is one of the strangest concepts in all of science. It does not shine like stars, does not glow like hot gas, and does not reflect a light in any way. To telescopes, it is completely invisible, and yet dark matter outweighs every star, planet, and gas cloud in the entire galaxy. Astronomers believe that most of the Milky Way's mass, perhaps more than 80% of it, is locked away in this invisible material. The dark matter halo stretches outward for hundreds of thousands of light years, forming a gigantic, unseen web around the galaxy. The proof of its existence lies in how it pulls on the stars. If we only counted the visible matter, the stars, gas and dust, the Milky Way's spiral arm should spin much slower than they do. But they do not. They spin far faster, as though an enormous hidden weight is keeping them bound together. That hidden weight is the dark matter halo, quietly holding the galaxy in place. Our own solar system lies within the lower portion of this halo. Above us is not empty silence, but a strange region filled with rarefied gas, ancient wandering stars, and the invisible grip of dark matter. The airless emptiness here is so thin that its density is far lower than even the best vacuum chambers scientists can create in laboratories on Earth. Yet, despite being so ghostly and empty, the halo is vital to the galaxy's stability. It acts almost like a cosmic cushion, pressing gently on the Milky Way and helping it keep its shape. Without the halo's influence, small companion galaxies might slowly drift away into the endless wilderness of intergalactic space. The halo keeps them bound to us, circling like distant moths around a central flame. In recent decades, astronomers discovered that the halo has another hidden layer, one they call the circumgalactic medium. This is a vast ocean of scorching hot gas that surrounds the Milky Way like a hazy veil. It is almost invisible to ordinary eyes, but it glows faintly in X-ray light. Scientists have detected it not by direct pictures, but by the way it interferes with light from even more distant objects such as quasars. The temperatures of this gas are astonishing. They range from about 1 million to 10 million degrees on the Kelvin scale, so hot that no solid object could survive inside it. In fact, astronomers believe that this cloud may contain more matter than all the stars in the Milky Way combined. The gas is not spread evenly. It tends to cluster above and below the galactic disk, almost as if the Milky Way were breathing fire out of its poles. Studying this circumgalactic medium is incredibly difficult. Unlike a star or a planet, it cannot be photographed clearly. Instead, scientists must assemble a picture of it from faint clues, the way it bends radio waves, the way it scatters light, and the delicate absorption lines it leaves on beams of light travelling from even farther galaxies. To investigate this fiery halo, astronomers have launched special space observatories. Satellites such as ROSAT, Chandra and XMM Newton have been essential in collecting data about the hot gas, and the future holds even more promise. Planned missions such as ExoRISM and Athena are designed to provide sharper, more detailed observations of this mysterious region, hopefully unlocking secrets that are still hidden from us. It would be easy to think of the halo as a quiet container, passively surrounding the Milky Way. But the truth is far more dramatic. The halo is alive with energy and violence. Rising high above and below the galactic centre are two colossal structures called the Fermi bubbles. These bubbles are not small, they stretch for tens of thousands of light years, dwarfing our entire solar system many times over. They are made of searing gamma-ray radiation, the most energetic form of light in the universe. Their discovery shocked astronomers who realised that such enormous features must have been created by incredibly powerful events. The leading idea is that these bubbles were blown into existence by the central black hole of the Milky Way. This black hole, a monster with a mass of millions of suns, occasionally erupts in violent outbursts. Long ago, it may have swallowed a massive cloud of gas or even a small galaxy, releasing titanic blasts of energy that carve these two glowing lobes into the halo. The Fermi bubbles prove that the halo is not static. It can be disturbed, reshaped, and stirred up by forces that lie deep within the galaxy's heart. And we, on our small planet Earth, are not separate from this story. Our solar system floats within the galactic halo. The Sun and its planets orbit the Milky Way's centre at a distance of about 26,000 light-years. But this orbit is not a flat path. Instead, the solar system bobs gently up and down through the galactic plane, like a ship riding the swells of a cosmic ocean. One complete up and down cycle takes between 30 and 35 million years. Over such long spans of time, our solar system passes through different layers of the halo, sometimes through denser regions, sometimes through thinner ones. Some scientists have wondered if these passages might influence events on Earth. Could the solar system's journey through the halo affect the flow of comets, sending more of them toward the inner solar system? Could it even play a role in long-term climate shifts or mass extinctions? These ideas remain uncertain, but they remind us that the halo is not just a distant abstraction. It may be quietly influencing the story of life on Earth itself. The galactic halo is, in many ways, the memory of the Milky Way. Its wandering stars and ancient clusters carry records of cosmic collisions that built the galaxy from fragments. Its vast store of dark matter provides the hidden weight that keeps the spiral arms spinning in their graceful dance. Its scorching circumgalactic medium surrounds the Milky Way in a fiery shroud, while its Fermi bubbles testify to the eruptions of a restless central black hole. And all the while, it cradles our solar system within its boundaries, binding us into the galaxy's family with a grip that is invisible yet undeniable. Far from being an empty nothingness, the halo is a living archive of cosmic history, a guardian of the galaxy's shape, and a reminder that even the emptiest-looking corners of the universe are filled with secrets. It is everywhere around us, silent but powerful, patiently waiting for us to uncover more of its mysteries. When people usually think about what lies above the universe, the imagination tends to stay fairly close to home. We often picture the restless streams of solar wind endlessly blowing outward from the sun, or the occasional lonely planet wandering through space without a star to call home. Others may think of the faint and delicate mist of cosmic dust. the powder of stars past, gently floating in the darkness. These are all familiar and local things, still part of the space that feels like our neighbourhood. But if we step back, far, far back, and try to look at the universe not from the scale of planets or stars, but from the scale of the grandest structures ever discovered, then the meaning of the word above changes completely. Above does not simply mean the sky over our heads. It begins to mean something unimaginably vast. Entire oceans of galaxies, enormous rivers of matter, and invisible currents of gravity that shape the universe itself. Our solar system is only a tiny speck inside the Milky Way galaxy, a vast spiral of stars. But the Milky Way itself is not the end of the story. Our galaxy, along with countless others, belongs to something so enormous, so overwhelming in size, that it dwarfs everything we can see with the naked eye. Astronomers call this giant realm the Laniakea supercluster. Its name comes from the Hawaiian language and means immense heaven, and the name could not be more fitting. Laniakea is not just a random scattering of galaxies floating in all directions. It is a true structure of the cosmos, a kind of cosmic basin where the invisible pull of gravity has gathered matter together. To imagine it, picture rivers on Earth flowing across landscapes. Water never flows randomly. It follows the curves of valleys and mountains, always finding its way toward the sea. In the same way, galaxies in Laniakea flow along invisible paths shaped by gravity, slowly but steadily drifting toward deeper regions of attraction. This supercluster is staggering in size. It stretches across more than 500 million light-years. To grasp what that means, remember that light travels faster than anything else in the universe, racing through space at nearly 300,000 kilometers every second. And yet, even at this breathtaking speed, light would need 500 million years just to cross Laniakea from one side to the other. Within this span lie thousands upon thousands of galaxies, including our own Milky Way, all caught in a shared journey, like leaves drifting on the same vast current. At the very heart of Laniakea lies something even more mysterious, a hidden gravitational giant called the Great Attractor. We cannot see it directly. It does not shine with stars, yet its influence is undeniable. It acts like a cosmic whirlpool, pulling galaxies inward, bending their paths toward itself. The Milky Way, our neighbouring Andromeda galaxy, and hundreds of other galaxies in the Virgo cluster are all being slowly drawn toward this unseen source of gravity. They are like small streams feeding into the greater river of Laniakea. The recognition of Laniakea in the year 2014 marked a turning point in astronomy. Before this discovery, astronomers described superclusters mostly by their appearance, outlining them as shapes of light on star maps. But Laniakea was not revealed by its glow. It was uncovered through something far deeper. The study of peculiar velocities, the small motions of galaxies beyond the general expansion of the universe. By measuring how galaxies drifted relative to each other, scientists noticed a pattern. They found that many galaxies which once seemed separate were actually connected, threads of motion weaving together into one vast gravitational flow. In this way, the outline of Laniakea emerged not drawn by light, but traced by the invisible hand of gravity itself. From our position inside the Milky Way, much of Laniakea's mass appears to lie above the plane of our galaxy, stretching northward into the sky. It reaches toward constellations such as Virgo, Centaurus, and Hydra. When we look upward into those directions, we're not just gazing at scattered stars, we're peering into the densest regions of our greater cosmic home. Astronomers have long noticed that the northern half of the sky reveals a more complex and richer cosmic web than the southern half. Many of the largest rivers of galaxies flow northward, carrying with them the evidence of this grand gravitational order. This alignment is not only poetic, it is practical. Because so much of Laniakea's density lies above, many of the world's greatest observatories point their instruments toward those skies. Projects like the Sloan Digital Sky Survey, the 2-micron All-Sky Survey, and the Cosmic Flows Project focus heavily on the northern hemisphere. In contrast, the southern skies are often harder to study, clouded by the thick band of our own galaxy's stars and dust. Fortunately, astronomers have found windows such as the northern galactic cap, where the view opens more clearly. Through these cosmic windows, telescopes peer past the Milky Way into the emptier stretches beyond. where the grand architecture of galaxies and voids can be traced. Within Laniakea, astronomers have mapped vast cosmic filaments, long, thread-like structures where galaxies gather like beads on a string. These filaments act as highways of matter, guiding galaxies toward major hubs of gravity. Some of these hubs include the Great Attractor itself, as well as the enormous Shapley supercluster, which also lies inside Laniakea's domain. Our own Milky Way is moving along one of these filaments, steadily climbing upward into the northern reaches of the supercluster. It is as if our galaxy is scaling the backbone of this immense structure. Evidence of this motion even comes from the oldest light in the universe, the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light has a subtle temperature difference across the sky, a feature called the dipole anisotropy. That difference reveals that the solar system itself is moving upward, drawn toward the enormous mass at the centre of Laniakea. This shows that our journey is not a mere drawing on a star chart. It is a real and measurable voyage. Yet, as vast as our understanding has grown, we are still only beginning to grasp the full nature of Laniakea. Ordinary telescopes cannot capture its boundaries because its structure is not defined by light, but by the invisible influence of gravity. Mapping it requires not only powerful instruments, but also sophisticated models and computer simulations. In the coming years, ambitious new projects such as the Euclid mission, the Vera Rubin Observatory, and the Nancy Grace Roman Space Telescope will carry this work forward. They will reveal how groups of galaxies interact with mysterious dark matter, and how these immense gravitational rivers have changed and evolved across billions of years. But perhaps the deepest lesson of all is this: Laniakea reminds us that we are part of something unimaginably greater. The Milky Way is not drifting aimlessly through space, nor is our solar system wandering without direction. We are being pulled, guided along invisible highways carved by gravity itself. We are travelling upward and inward, toward a destination we cannot yet fully see or understand. Above the universe lies more than just scattered stars and drifting dust. Above us stretches the grand current of the immense heaven, a journey of galaxies upon galaxies, all flowing together into the unknown. It is a reminder that our home is not only Earth, not only the solar system, not only even the Milky Way. Our true home is this vast and mighty structure of the cosmos, and we are all passengers on its endless voyage. When we look at the universe, we imagine the familiar family of planets circling the Sun, Mercury glowing closest, Venus wrapped in thick clouds, Earth with its blue oceans, Mars rust-red and dry, and then the mighty gas giants with their swirling storms and icy moons. Beyond them lies the dwarf planet Pluto, drifting in the darkness of the Kuiper Belt. For many, Pluto once marked the very edge of our Sun's kingdom, but in truth, that was never the end. Far beyond the Kuiper Belt, past the scattered disk where icy fragments wander like cosmic exiles, lies one of the most mysterious and distant structures ever imagined, the Oort cloud. Imagine a giant, ghostly sphere, made not of light or gas, but of frozen bodies, comets, icy rocks, and debris left behind from the dawn of the solar system. This shell, sometimes compared to a bubble or a cage of ice, is thought to surround the Sun on all sides, marking the very edge of its gravitational influence. The Oort cloud is ancient, older than human history, older even than the Earth itself, for it was formed when the solar system was still in its infancy, billions of years ago. Inside it are believed to rest trillions upon trillions of frozen wanderers, each a relic of creation, waiting silently in the cold dark until some disturbance hurls them inward toward the Sun. But there is a question rarely asked: what lies beneath it? The Oort cloud is usually imagined as a vast, symmetrical sphere, but what about its underside, its southern half that dips below the solar system's main plane of planets, stretching into the far reaches of southern space? Could it be different from the top half we usually picture in our minds? Could the bottom hold secrets untouched for billions of years, or perhaps even relics from other stars entirely? To grasp the sheer size of the Oort cloud, we must use a special unit of distance known as the astronomical unit, or AU. 1 AU is the average distance between the Earth and the Sun, about 150 million kilometres. For everyday scales, that is already an unimaginably vast gap. Yet the Oort cloud begins not at 1 AU, or even at 100 AU, but at around 2000 AU from the Sun, and may extend as far as 100,000 AU. Let us put that into perspective. Pluto orbits the Sun at about 40 AU. Humanity's most distant spacecraft, Voyager 1, has been travelling outward since the year 1977 and has already passed beyond the edge of the heliosphere, the Sun's protective bubble. Even so, Voyager 1 is only around 160 AU from home. That means it has not even scratched the surface of the Oort cloud. To Voyager, the cloud still lies like an unreachable horizon. The scale is so immense that if the Sun and its planets were shrunk down to the size of a coin sitting in your palm, the Oort cloud would stretch outward across an entire city. It is a frontier not only of distance but also of imagination. No telescope has ever seen the Oort cloud directly. It is too faint, too spread out, and too far away. Its icy fragments are small and reflect little sunlight. For us, the Oort cloud is an invisible structure, yet we know it exists. Its presence is betrayed by comets, icy messengers that come screaming into the inner solar system on highly stretched orbits. Unlike short-period comets that return every few years, these long-period comets come from random directions, some tilted at sharp angles, others even moving backward compared to the orderly paths of the planets. Such wild trajectories can only be explained if they originated in a faraway spherical reservoir, the Oort cloud. Some comets even appear to come from the underside, the southern half of this icy sphere. Famous examples include Comet Hale-Bopp in the year 1995 and Comet C 2017 K2 Pan-STARRS. Both entered the solar system on sharply slanted paths, almost as if they were tumbling down from below. These comets, like postcards from the deep, offer indirect proof that the Oort cloud is not a flat disk, but a true three-dimensional sphere wrapping all around the Sun. This symmetry brings us to a new puzzle. Is the Oort cloud truly the same everywhere, or is its bottom half, the underside, different? Some scientists believe the southern regions may indeed have unique features. One reason lies in the position of our solar system within the Milky Way. The Sun does not sit perfectly centred in the galaxy's flat disk. Instead, it hovers slightly above it. Because of this, the lower part of the Oort cloud may feel the pull of the galaxy's gravity differently. Over billions of years, such an uneven tug could stretch or compress the southern hemisphere in ways not mirrored in the north. If so, more comets might drift inward from the underside than from the top, making the southern Oort cloud a livelier, more restless region. The Oort cloud does not float undisturbed. As the Sun journeys around the centre of the Milky Way, taking more than 200 million years for a single orbit, it encounters other stars. Some pass close enough to disturb the Oort cloud with their gravity, stirring up its icy residents and sending them cascading toward the inner solar system. About 70,000 years ago, a faint red dwarf called Schultz's star drifted within less than a single light-year of the Sun. Though faint and barely noticeable in our skies, its proximity was enough to tug at the Oort cloud, likely shaking loose comets, perhaps especially from its southern half. In the future, around 1,300,000 years from now, another star, Gliese 710, will come alarmingly close, within only about 0.06 light-years. Such a flyby will almost certainly scatter countless comets inward. Many of these may emerge from the underside of the Oort cloud, raining down like icy arrows from the southern skies. But stars are not the only cosmic players. Some scientists speculate that the Oort cloud may also be shaped by something far more mysterious: dark matter. Dark matter is an unseen substance that makes up most of the mass of the universe. It does not shine, it does not absorb light, and it cannot be touched. Yet its gravity is real, sculpting galaxies and holding them together. Some models suggest that dense clumps of dark matter may occasionally pass through the outskirts of the solar system, especially from less observed directions such as the underside. These encounters could jostle the Oort cloud and send comets tumbling inward in waves. If such showers were large enough, they might even cause extinction events on Earth, just as asteroids and comets have done in the past. Though speculative, this idea adds an eerie layer of danger to the Oort cloud's underside, an unseen realm possibly linked to the great cycles of life and death on our planet. Another fascinating theory suggests that the underside of the Oort cloud may contain not just native solar system objects, but also outsiders, icy travellers from other stars. Billions of years ago, when the solar system was young and chaotic, countless small planetesimals were thrown outward by the giant planets. Some escaped entirely, while others became trapped in the Oort cloud. During this same era, the Sun was part of a dense star cluster, crowded with other newborn stars. It is thought that some of their icy debris may have drifted close enough to be captured by the Sun's gravity. If so, the Oort cloud, especially its southern regions, might be sprinkled with alien comets, frozen fossils from stars long gone. These alien comets would be chemically different, carrying isotopes, minerals, and volatile elements unlike those found in comets formed near our Sun. Each one would be a messenger not just from the solar system's edge, but from entirely different stellar nurseries. If we could one day study them, we would be holding pieces of other stars in our hands. The greatest challenge is distance. No spacecraft has ever gone anywhere near the Oort cloud. No telescope has glimpsed it. How then can we know its underside at all? The answer lies in comets themselves. Every comet that plunges into the solar system is like a note from the edge of creation. By charting their paths, astronomers can trace back where they came from. Comets that fall from steep southern angles are clues about the underside. By analysing their chemical fingerprints, scientists can compare whether southern comets are different from northern ones. New instruments will greatly enhance this detective work. The Vera C. Rubin Observatory, expected to begin its survey soon, will discover thousands of new long-period comets in the coming decades. Many of these will emerge from the southern skies carrying whispers from the underside of the Oort cloud. Each discovery will bring us closer to answering whether the bottom truly differs from the top. Someday, we may go there ourselves. NASA has discussed concepts for an interstellar probe, a spacecraft that could travel thousands of astronomical units outward, far beyond the planets. If launched, it could eventually skim the inner edges of the Oort cloud. Such a mission would be able to measure dust grains, magnetic fields, and the composition of particles drifting through space, offering the first direct evidence about the cloud's nature. By comparing data from above and below, we could finally discover whether the underside of the Oort cloud hides differences invisible from afar. This would be a journey into the oldest frontier of the solar system, a place untouched for billions of years, a place where the sun's power fades and the galaxy's forces begin. The underside of the Oort cloud is more than just a region of space. It is a frontier where our understanding falters, where speculation and science dance together. It may hold comets that carry the fingerprints of alien stars. It may be stirred by passing suns and sculpted by invisible dark matter. It may be lopsided, restless, and alive with comets waiting to fall. For now, it is silent, hidden in darkness. But with every new comet, with every future mission, we inch closer to hearing its story. The Oort cloud's underside is not just the bottom of a sphere. It is a doorway to the unknown, the edge of the sun's dominion, and perhaps the key to understanding the deepest cycles of our solar system and our galaxy. Deep beneath the smooth circular path that our solar system follows around the Milky Way lies something immense, ancient, and impossible to ignore: the galactic core. This is the very heart of our galaxy, the gravitational anchor that holds everything together. It is not an empty place, nor is it quiet. Instead, it is a restless, crowded, glowing, and often violent region where countless stars burn, where magnetic fields twist and tangle like invisible ropes, and where, at the very centre, there lurks a giant black hole known as Sagittarius A star. Our solar system is not sitting still inside the Milky Way. Like a tiny speck caught in a whirlpool, it moves along with the rest of the galactic disk, circling the centre in a broad, nearly flat orbit. One complete trip around the galaxy takes an unimaginably long time, about 225 million years. That means the last time we were in the same place in our orbit, the dinosaurs were walking the Earth, but our solar system's journey is not perfectly smooth or level. Gravity never allows such perfection. Instead, the solar system bobs gently up and down as it travels, the way a ship rises and falls with the swell of an ocean. Astronomers have learned that this vertical oscillation happens on a cycle of roughly 30 to 35 million years. Every so often, we cross the thin midplane of the Milky Way, rise high above it, and then sink back down again, pushed and pulled by the combined tug of stars, gas clouds, and even the mysterious invisible substance we call dark matter. At this very moment, Our solar system sits about 25 to 30 light years above the galactic midplane. We are slowly drifting downward, ever so gently, in a movement so subtle that no human being could ever feel it in a single lifetime. And yet this vertical motion is not meaningless. It plays a crucial role in how material circulates through the galaxy. Gas, dust, even entire star systems can migrate above and below the disk, slowly funneling toward the centre in ways that astronomers are only beginning to understand. Imagine, for a moment, that you could release an object from our solar system's current position and simply let it fall downward toward the centre of the galaxy. At first, it would cut through the galactic disk itself, the broad, flat region where most of the stars, glowing nebulae and rivers of dust reside. This is the Milky Way as we see it stretched across the night sky, a dazzling band filled with so many suns that their light blends into a misty glow. As the falling object continues deeper, the pull of gravity grows ever stronger. The closer it moves towards Sagittarius A star, the more the invisible hand of gravity tightens its grip. Our Sun itself lies about 26,000 light-years away from the galactic centre, so the object would have an astonishingly long way to fall. Each passing light-year would increase its speed. Space-time itself, the very fabric of reality, bends inward, steepening the descent as though the object were sliding down a vast invisible funnel. This imagined plunge would never be a simple straight drop. The Milky Way is not a still pond, it spins, and like a whirlpool, its inner regions rotate faster than the outer edges. Anything falling inward from above or below would be swept into that spin. Instead of racing directly toward the centre, the object would spiral, caught in the swirling motion of the galaxy's arms. Its path would carry it through regions far denser than anything near Earth, areas where stars are packed so closely together that the night sky would blaze like a jewel box. The spiral descent would carry it through the galactic bulge, a thick rounded cloud of ancient stars that shines reddish with age. Here, star density can be hundreds of times greater than in our quiet neighbourhood near the Sun. Along the way, the object would pass vast molecular clouds, cold and dark, where new stars are quietly gestating. It would weave through magnetic filaments, invisible but powerful, and encounter the violent chaos of the central molecular zone, where star birth and star death occur side by side in an ongoing cycle of creation and destruction. One particularly fascinating aspect of imagining a fall from beneath the galactic disk is that the southern half of our galaxy, the sky below the disk, has long been less studied than the northern half. For centuries, most of the world's great observatories were built in the northern hemisphere, which meant astronomers had a clearer view of the stars above the disk than those below it. That imbalance is changing. New instruments in the southern hemisphere, such as the Vista telescope in Chile, have begun mapping the hidden southern skies. Soon, the powerful Vera C. Rubin Observatory will join them, giving us breathtakingly detailed views of regions we have only glimpsed until now. For the first time in human history, we will be able to study the southern route of this imagined fall toward the galactic centre with the same precision as the north. As the object descends further, it would pass through increasingly exotic environments. Matter and radiation become denser. Magnetic fields twist tighter and knot into chaotic patterns. Neutron stars, the collapsed remnants of massive suns, lurk like embers of cosmic violence. Stellar collisions occur, and smaller black holes roam unseen, each a trap hidden in the dark. And finally, at the centre of it all sits Sagittarius A star, a supermassive black hole with a mass equal to about 4,300,000 suns. Nearly motionless, it anchors the galaxy with its immense gravity, shaping the paths of stars even tens of thousands of light-years away. To approach it is to enter a realm where light itself bends, where time slows, and where space takes on unfamiliar shapes. Although Sagittarius A star is relatively quiet now, scars in the sky suggest it was not always so calm. Astronomers have discovered evidence that a few million years ago, it erupted in vast outbursts, blasting jets of energy far into space. The remnants of those outbursts still remain today as two enormous bubble-shaped structures, the Fermi bubbles, that stretch high above and below the galactic plane. They are silent witnesses to the black hole's once fiery past. Close to the black hole lies the innermost stable circular orbit, a kind of invisible edge. Any object spiraling inward that crosses this line can no longer resist. It cannot hold a safe orbit. It falls. Yet in truth, most objects never survive that long. Long before reaching this boundary, they are shredded by tidal forces, roasted by radiation, or torn apart by magnetic storms. This grand thought experiment is not just poetic fancy. Astronomers take the idea of falling toward the galactic centre very seriously. The vertical motions of stars and gas, their rising and sinking above and below the galactic disk, are key to understanding how the Milky Way evolves over billions of years. These motions explain how stars drift to new neighbourhoods, how gas clouds spread out or collapse, and how, over time, matter is funneled toward the black hole at the centre. When enough material builds up near Sagittarius A star, it can trigger new outbursts of energy, colossal events powerful enough to reshape the galaxy itself. In this way, the Milky Way is not a calm, flat pinwheel of stars circling forever in neat paths. It is a living, restless system where matter constantly collides, migrates, and sometimes plunges headlong into the heart of darkness. This same story of rising, falling, and spiralling inward can be seen on a much smaller scale right here in our solar system. Surrounding the planets is a thick cloud of dust that lies mostly along the flat orbital path known as the ecliptic. For a long time, astronomers thought this dust was confined to a single thin layer. But thanks to powerful infrared space telescopes such as IRIS and COBE, we now know that the dust forms multiple layers, some stretching far above and below the main plane. The dust is slowly being pulled inward by the Sun's gravity, but the planets also sculpt its distribution with their own gravitational nudges. On top of that, a subtle effect known as Poynting-Robertson drag makes the dust spiral inward, closer and closer to the Sun, like grains of sand sliding down a whirlpool. Along the way, many of these dust particles cross Earth's path, sometimes from above the orbital plane, sometimes from below. Even more astonishing is that not all of these dust grains were born here. Some are interstellar micrometeoroids, tiny fragments of matter that come from outside our solar system altogether. These wanderers rush in on hyperbolic trajectories, entering the heliosphere from all directions. Measurements from spacecraft such as Ulysses, Galileo, and Cassini show that a significant fraction of this incoming dust comes from the direction of the galactic south, slicing through our system from below the planetary plane. These interstellar grains are unbelievably small and fast, so small that they are almost invisible, yet so quick that they strike with tremendous force. Most are too tiny to punch holes in spacecraft, but over long stretches of time they can cause serious damage. They scratch thermal blankets, blur lenses, and sometimes pierce fragile solar panels. The International Space Station treats this threat with the utmost seriousness. Its modules are wrapped in protective shielding, and its orientation is carefully adjusted to minimize exposure during meteor showers. The smallest fragments of dust may not look like much, but when you are moving at orbital speeds, even a speck can strike like a bullet. To study and predict these impacts, scientists use advanced instruments such as DRAGONs, short for Debris-Resistive Acoustic Grid Orbital Navy Sensor. This device can detect dust impacts in real time, helping researchers map the angles and speeds of incoming micrometeoroids. Many of these measurements confirm that a large portion of them do indeed come from the southern sky, striking from beneath Earth's orbital plane. Future missions will face even more extreme challenges. Spacecraft like Solar Orbiter, which already travels outside the main planetary plane, are beginning to sample dust in unusual orbits. More ambitious missions that venture toward the distant Oort cloud, the icy shell at the edge of our solar system, will encounter micrometeoroids unlike any seen near the inner planets. Studying these grains, especially those that fall in from unusual angles, is teaching us that our solar system is not a neat flat pancake of planets circling the Sun. Instead, it is a three-dimensional, constantly shifting stage where dust and debris float, collide, fall inward, and reshape the cosmic environment around us. When most of us think about the universe, our minds usually go straight to the familiar. The round paths of planets circling the Sun, the long looping journeys of comets, and the steady pull of our star that seems to hold everything together. It is a picture of harmony, where orbits follow clear rules, and gravity is the quiet conductor keeping time. But beneath this familiar surface, there may be something far stranger, far more hidden, and far more fascinating. Astronomers and mathematicians are beginning to uncover what could be described as a secret architecture beneath the universe's stage, a delicate network of invisible gravitational corridors. These corridors are not physical tunnels or tubes that one could enter. They cannot be seen with even the most powerful telescope. Instead, they are subtle highways made of gravity itself, sculpted by the combined pull of the Sun, the planets, and even the greater Milky Way galaxy in which we live. They form natural routes through space, lanes where an object can move with very little effort, almost as if it is sliding along an unseen stream. To imagine them, think of a great river winding its way through valleys. The water does not carve the path with brute force in a single moment. It follows the gentle slope of the land, flowing where gravity allows. These cosmic highways are the space equivalent of such riverbeds, shaped not by water, but by the delicate balancing act of gravity. For a long time, scientists have studied similar paths on the flat plane where the planets circle the Sun, a region known as the ecliptic. In this thin slice of space lies something called the interplanetary transport network. This is a system of invisible paths, shaped in part by what are known as Lagrange points. These are special spots where the tug of the Sun and a planet cancel each other out, producing little pockets of balance. In such places, a spacecraft, a comet, or even a drifting rock can hover, orbit gently, or slip into controlled chaotic movement. These points act as gateways, and together they create webs of motion, routes that link planets, moons, and other bodies together. But for centuries, our gaze has mostly been locked on this thin, flat sheet of orbits. What happens if we tilt our perspective? What happens if we stop looking only at the flat plane and instead explore the vertical dimension, the space above and beneath the solar system's disk? In recent years, mathematicians and astronomers have done just that. They have turned to a famous idea in celestial mechanics known as the restricted three-body problem. This problem explores how three objects, a star like the Sun, a planet such as Jupiter, and a much smaller traveller like an asteroid or a spacecraft, interact with each other's gravity. From this, it becomes clear that gravity is not a simple flat surface. Instead, it folds, curves, and dips in three dimensions. Imagine a great invisible landscape made not of soil and stone, but of gravitational energy, filled with valleys, ridges, and mountain passes. These curves open up secret routes not only across the flat planetary plane, but also far above it and deep below it. In these underexplored regions, gravity creates valleys that function like downhill slopes. Just as rivers guide water downward, these valleys may act as energy-saving lanes that guide objects with minimal force. A spacecraft that slips into one of these lanes could travel extraordinary distances while consuming only a small amount of fuel. Nature itself provides the push. This is not mere theory. In fact, space missions in our own time have already begun to take advantage of these hidden lanes. NASA's Lucy mission, designed to visit Jupiter's Trojan asteroids, and the European Space Agency's ambitious mission called JUICE, which is aimed at Jupiter's icy moons, both use gravitational highways to travel more efficiently. Instead of relying solely on engines and fuel, they surf along the natural contours of space. Yet the most intriguing idea of all is that these invisible corridors may also run deep beneath the Sun, in regions less disturbed by the pull of large planets. Such hidden routes could act like funnels, channeling asteroids, comets, and perhaps even fragments of interstellar material toward the centre of our solar system. Imagine an icy body nudged from the faraway Oort cloud at the edge of the Sun's influence. Instead of tumbling randomly, it might quietly slide inward along one of these invisible lanes, guided not by forceful tugging but by gentle encouragement, much like a leaf gliding along a calm stream. At the very centre of this grand system is of course the Sun. Its immense weight bends space itself, curving the very fabric of reality. And when the Sun's influence joins with the pull of the galactic mid-plane, the dense flat sheet of stars, gas and dust that makes up the middle of our Milky Way, an even grander design comes into view. The two together shape gradients and slopes that open low-energy routes in all directions, upward and downward, inward and outward. Picture, for instance, a spaceship placed beneath the Sun, aligned with one of these gravitational lanes. In theory, it could be nudged outward, riding along a natural escape path. With very little fuel, it could let gravity itself fling it from the solar system, sending it sailing into the southern sky and out toward the countless galaxies beyond. These hidden corridors may not only be tools for the future, they may also be the reason we're here at all. Billions of years ago, when the solar system was young and still forming, icy bodies and planetesimals scattered from the outer disk may have rained downward through these gravitational lanes. Over immense stretches of time, this slow but steady delivery of material may have shaped the inner planets, bringing water, ice, and essential minerals. The fact that some worlds have unusual tilts, or slightly uneven mixtures of elements, might even be the fingerprints of this ancient vertical infall, where southern streams of debris shape the very face of our planetary family. But these corridors are not always smooth highways. Sometimes they act as traps. Small pieces of rock, drifting dust, or even artificial fragments from human spacecraft can find themselves caught in these pathways, circling the Sun in unusual, temporary orbits. This may be the reason why astronomers occasionally find strange groups of rocks moving together or clouds of dust hovering in tilted, hard-to-detect tracks. Some of these trapped wanderers may be incredibly ancient, left suspended for billions of years, quietly held in place by the patient and invisible hand of gravity. Understanding this hidden architecture of motion is not just a matter of curiosity. It may be vital for humanity's future in space. Missions to the Kuiper Belt, journeys toward interstellar space, or even strategies to deflect dangerous asteroids away from Earth may all depend on our ability to map and use these gravitational lanes. Instead of burning vast amounts of fuel, we might one day learn to glide across the solar system as naturally as a bird riding a current of air. And if we can imagine this, perhaps others have too. If intelligent civilizations exist elsewhere among the stars, they might have long ago discovered and mastered these gravitational highways. Instead of building enormous engines, they may travel quietly along the hidden seams of gravity, slipping between star systems like sailors following invisible trade winds. Perhaps the universe is already threaded with such ancient routes, unseen by most, yet waiting patiently for us to recognize them. These hidden pathways, sculpted by the slow and silent work of gravity, remind us of something profound. Space is not empty. It is structured, patterned, and alive with subtle possibilities. And as we learn to see these invisible rivers for what they are, we may also learn how to follow them, whether to understand our origins, to protect our world, or to set sail toward the stars. Far beneath the familiar plane of our solar system's path through the Milky Way, there is a hidden world of space that is stranger and quieter than most people imagine. At first glance, one might think that the great void between the stars is simply empty. But in truth it is not. Even in the loneliest regions of interstellar space, there lingers a faint fog of gas and dust. This thin veil is what our solar system is currently travelling through, and astronomers call it the local interstellar cloud, often shortened to LIC. The local interstellar cloud is not a thick or heavy cloud like those we see in the sky on Earth. Instead, it is a delicate blend of partly charged hydrogen and helium atoms, so thin that it would be invisible to our eyes even if we floated right in the middle of it. This cloud stretches for about 30 light-years across space, impossibly vast to us, yet small when compared to the enormous scale of our galaxy. The LIC itself is only a fragment of a much larger structure known as the local bubble, a gigantic cavity in the interstellar medium. The local bubble is a region carved out long ago by violent stellar explosions, and within its emptiness drifts just a few fragile wisps of material. Among them, our modest LIC. But the story becomes even more fascinating when we look downward, toward the southern direction of our galaxy, beneath the thin plane of the local interstellar cloud. There, astronomers have discovered an even stranger environment, a region that is thinner, emptier, and less crowded with matter than the LIC itself. This underbelly of space is what scientists sometimes call the intercloud medium. Imagine the galaxy as a patchwork quilt. Some parts of the quilt are thick with fabric. These represent the dense clouds of gas and dust, where new stars and planets may eventually form. Between those thicker patches, however, are the seams, the spaces in between. These seams are not completely empty, but they are astonishingly sparse compared to the clouds around them. That is what lies beneath our current path. a vast stretch of extremely low-density interstellar material. To understand how different these places are, consider their densities. The local interstellar cloud has a density of about 0.3 atoms per cubic centimetre. That already sounds almost like nothing, but in cosmic terms it is still noticeable. By comparison, the spaces below the LIC can drop to around 0.05 atoms per cubic centimetre, or even less, so empty that it is closer to a vacuum than almost anywhere else nearby. These differences may sound trivial, but they are not. They shape the very edge of our solar system's protective bubble, the heliosphere. The heliosphere is created by the solar wind, the constant stream of charged particles that flows outward from our Sun. Where this solar wind finally meets the interstellar medium, its push is balanced by the pressure of the surrounding gas, forming a great invisible boundary called the heliopause. Now here is the remarkable part. If our solar system drifts into a region of lower density, the heliosphere can swell outward and expand because there is less outside pressure holding it back. If, instead, we wander into a denser region, the heliosphere is squeezed inward. That means the size and shape of the bubble protecting Earth and the other planets is not fixed. It breathes with the galaxy, expanding and contracting as we cross into different environments. Many models suggest that right now, we're nearing the very edge of the local interstellar cloud. If that is true, then in the not-so-distant future we may slip into one of those thinner, emptier regions beneath it. If this happens, the heliosphere will expand, and more cosmic rays, those high-energy particles launched from distant stars and galaxies, will be able to reach deeper into our solar system. The effect might be subtle, but it is real. More cosmic rays could mean stronger interference with satellites and spacecraft electronics, as well as increased health risks for astronauts on long missions beyond Earth. But how do we even know what lies below, when the matter is so thin that it is almost undetectable? The answer comes from light, specifically ultraviolet light from nearby stars. When this light travels through interstellar space, some of it is absorbed by the gas it encounters along the way. By carefully studying these faint absorption lines, astronomers can piece together a map of where the gas is thicker, where it is thinner, and where the clouds end. Instruments like the Hubble Space Telescope and the Far Ultraviolet Spectroscopic Explorer, FUSE, have been essential in this detective work. By studying stars south of the galactic plane, such as Alpha Centauri and Altair, astronomers can trace where the local interstellar cloud fades away into emptier territory. These stars act like beacons, their light carrying hidden clues about what lies between us and them. The origin of these empty stretches is dramatic. Millions of years ago, massive stars ended their lives in fiery explosions called supernovae. Each blast ripped through the interstellar medium, carving out cavities of thin, hot gas. Over time, several such explosions, likely occurring within the last 10 to 20 million years, merged to form the local bubble, a vast hollow about 300 light-years wide. Within this giant bubble floats only one small cloud, the local interstellar cloud itself, and beneath it lies a patch of space even emptier, a cosmic ghost town. This region is not filled with familiar molecules or heavy clusters of dust. Instead, it is occupied mostly by thin, hot plasma, atoms stripped of their electrons, glowing faintly as they drift in silence between the stars. If future missions, such as the proposed Interstellar probe or any successor to the legendary Voyager spacecraft, venture south of the heliosphere, this empty region is what they will encounter first. Those missions would give humanity its very first direct measurements of the intercloud medium, the hidden underbelly of our galactic neighbourhood. Though it seems barren, this low-density environment is rich in scientific value. Its emptiness allows certain things to happen that would be impossible in denser regions. For instance, radio waves and other long-range signals can travel much farther and more clearly through such thin plasma, since there are fewer particles to scatter or absorb them. Some scientists have even suggested that if advanced civilizations exist elsewhere in the galaxy, they might take advantage of these cosmic corridors to send messages across light years. A listening station placed in such a clear zone would be able to hear faint signals from extraordinary distances, like a radio tower on a high mountain peak catching voices carried by the wind. So what lies beneath the local interstellar cloud is not chaos or crowding, but silence. It is the quiet pause between bursts of galactic activity, the thin calmness carved by ancient supernovae and preserved by time. In this southerly direction, our solar system is gliding toward the emptiest neighbourhood it has ever known. Paradoxically, this emptiness may tell us more about our galaxy than the clouds themselves. It is the blank page on which the story of stars is written, the space between the lines of the Milky Way's great poem, and as our journey continues, this silent stretch may reveal secrets we never expected, not by being full, but by being nearly empty. High above the glowing plain of our Milky Way, and far below its crowded heart, rise two of the strangest and most breathtaking structures ever found in the galaxy. They are called the Fermi bubbles, two gigantic towers of invisible light that span across tens of thousands of light years. They shine with a force so intense that it slices across the galaxy like deep scars in the heavens. Astronomers first discovered these bubbles in the year 2010, when NASA's Fermi Gamma Ray Space Telescope spotted their ghostly glow. From that moment on, they became one of the greatest mysteries in modern astronomy. Two colossal beacons hanging over the galaxy, daring scientists to figure out how they were made. Each bubble rises about 25,000 light-years above and below the thin, starry disk of the Milky Way. To give a sense of scale, that is about the same distance between our Earth and the very core of the galaxy itself. Perfectly balanced on either side of the galactic plane, they look as though some immense cosmic sculptor had carved them with a blade of energy. And what fills them is even more astonishing: gamma rays, the brightest and most energetic kind of light in the universe. Gamma rays are not gentle or harmless like the warm glow of infrared or the penetrating but familiar rays used in X-ray machines. They are born only in the most violent and extreme events in the cosmos: black holes swallowing matter, stars exploding in titanic supernova, and particles slamming into one another at nearly the speed of light. That is the raw energy that floods the Fermi bubbles. But the wonder of these bubbles does not stop at their size or brightness. What truly makes them remarkable is how sharply defined they are. They do not fade softly into the background haze of the galaxy. Instead, they look like glowing towers that pierce straight into the galactic halo, the vast, ghostly sphere of stars, dark matter, and thin gas that wraps around the Milky Way. Inside the bubbles, astronomers have found blazing plasma heated to extreme temperatures, streams of high-energy particles moving at staggering speeds, and magnetic fields twisted into strange patterns. Even more astonishing, the bubbles may be expanding outward at nearly 1,000 kilometers every second. To compare, that is many times faster than anything we can create on Earth, and it means that in the span of a single heartbeat, the bubbles push outward by hundreds of kilometers. And yet, when scientists looked for the cause, they found no nearby supernova explosion and no region of star formation strong enough to have created them. This puzzle forced astronomers to think bigger, to consider an even more dramatic origin. The most convincing explanation points to the supermassive black hole at the very center of our galaxy, known as Sagittarius A star. Today, this black hole is quiet, lurking silently at the core of the Milky Way. But millions of years ago, it may have lived through a violent outburst, devouring great clouds of gas and spitting out enormous jets of particles. These jets, blasting upward and downward from the galactic center, could have carved their way into the thin halo above and below the galaxy, heating the gas and filling the sky with gamma rays. What we see today may be the fading echo of that ancient eruption. There is, however, another intriguing possibility. Perhaps it was not the black hole at all, but rather a starburst event, a time when stars were born in a furious rush near the galactic center. Such star-forming frenzies can drive out titanic winds of gas and radiation, shoving matter outward with enough force to carve bubbles into the galaxy. In this view, the Fermi bubbles are monuments not to a black hole's rage, but to a storm of countless newborn stars. Whichever story is true, the result is the same: two enormous lobes of energy, still glowing after millions of years, standing as silent reminders of a long-forgotten catastrophe in the heart of the Milky Way. The bubbles are also not simple in their structure. Within them, astronomers have detected layers of energy that shine in X-rays, first spotted by space observatories like Rosat and E Rosita. Along their sharp edges are boundaries that look like pressure fronts, cosmic shock waves, showing how the bubbles press against the thin halo gas, squeeze it, and change its temperature. In some places, the Fermi bubbles overlap with other vast features, such as the North Galactic Spur, revealing that the true sky is far more tangled and complex than it first appears. Even more fascinating, the bubbles may not be stable. Some studies suggest that they are shifting and changing, swelling outward, or fading depending on how the pressure inside them fights against the gas outside. Their perfectly symmetrical shape, however, points like an arrow back to the galaxy's core, leaving little doubt that the energy that birthed them came from deep within. Astronomers now wonder if our Milky Way is unique in this respect. If we have Fermi bubbles, might other galaxies have them too? Observations of galaxies such as Centaurus A reveal giant lobes of radio energy that look remarkably similar to the Fermi bubbles, hinting that such enormous outbursts may be a natural stage in the lives of spiral galaxies everywhere in the cosmos. From Earth, we cannot see the Fermi bubbles with our eyes. They remain invisible to ordinary vision, hidden from the gaze of stargazers, but through the eyes of gamma-ray telescopes they appear clearly, covering an immense stretch of the night sky. If human eyes could somehow see gamma rays, the familiar constellations would vanish, drowned out by the overwhelming sight. Instead, when we looked up at night, we would see two towering pillars of energy glowing above and below the Milky Way's shining band. They would stand like ancient monuments in the heavens, reminders of a titanic event that shook the very heart of our galaxy long ago. Far beneath the familiar flat plane on which our solar system rests, beyond the quiet drifting of comets and the faint haze of cosmic dust, lies something far stranger. It is not a wandering object or a random cloud of particles. Instead, it is something woven into the very fabric of the universe itself, a kind of scar, an icy wound imprinted on the oldest light we have ever seen. This strange scar appears in what astronomers call the cosmic microwave background radiation, or CMB for short. The CMB is a dim and ancient glow that fills the entire sky, the afterglow of the Big Bang, the great explosion that gave birth to space and time nearly 14 billion years ago. If you look at the universe in ordinary visible light, you will see stars, galaxies, and nebulae scattered about. But if you could tune your eyes to microwaves, you would see this faint, nearly uniform glow everywhere, as if the whole sky were painted with the same dull colour. But uniform does not mean perfect. Hidden within this ancient glow are tiny variations, slight warm patches and cool patches, differences of only millionths of a degree. These tiny ripples are actually very important. They are the seeds from which all galaxies, stars and planets eventually grew. Yet among all these subtle shifts in temperature, one region stands out as particularly bizarre. A vast cold patch that lies well below the galactic midplane, pointing toward the southern sky. Astronomers have named it the CMB cold spot. It rests in the constellation called Eridanus, a winding river of stars in the southern heavens, located far below the Sun's ecliptic path and even deeper beneath the flat disk of the Milky Way's galactic plane. This cold spot is not small. It spans nearly 5 degrees across the sky. To put that in perspective, that is about 10 times the width of the full moon as seen from Earth, a huge slice when compared to the entire CMB map. What makes it so striking is its temperature. This patch is about 70 microkelvin colder than the surrounding average. Now, by earthly standards, this difference does not sound like much. It would not even freeze a glass of water. But in the precise science of cosmology, where researchers measure tiny differences in ancient light, such a drop is like a chill wind cutting through the universe itself. It is a signal so unusual that it sends scientists into excitement and confusion in equal measure. The first hints of this cold patch came in the year 2004, when NASA's Wilkinson Microwave Anisotropy Probe, WMAP, revealed a detailed map of the CMB. Later, in the year 2013, the European Space Agency's Planck satellite confirmed the anomaly with even sharper precision. Both missions were designed to measure the faint glow of the early universe with extraordinary accuracy, and both showed the same thing. This patch of sky was too cold, too large, and too unlikely to be dismissed as mere random noise. Normally, small fluctuations in the CMB are expected. In fact, without them, galaxies and stars could never have formed. But the cold spot is a giant among these ripples, a deep hollow in the otherwise gentle pattern. Its size and depth are so unusual that the chance of it being a mere accident is extremely low. To make matters more convincing, it lies in the southern galactic hemisphere, an area of sky relatively free from interference like cosmic dust, radiation from our galaxy, or signals from nearby sources. That makes its existence even harder to explain away. So what could be causing this strange chill beneath our cosmic feet? One possibility is the simplest: pure coincidence. Perhaps in the chaotic froth of the early universe, a rare quantum fluctuation happened to grow larger than usual, leaving behind this unusually cold patch. Mathematically, this explanation makes sense, but emotionally and scientifically, many researchers are unsatisfied. The odds of such a large fluctuation occurring are so slim that it feels unsatisfying, like winning the universe's unlikeliest lottery. Another explanation is known as the supervoid hypothesis. According to this idea, the cold spot might be caused by a gigantic underdense region of the universe, a cosmic desert, hundreds of millions of light years across, containing far fewer galaxies than usual. If photons, the tiny particles of light from the CMB, had to cross such a supervoid on their way to us, they would lose just a little energy as they travelled. This loss, caused by something called the integrated Sachs-Wolf effect, would make them arrive slightly cooler than expected. Indeed, galaxy surveys have shown that there does seem to be an unusually empty region in the direction of the cold spot. But here lies the problem: it is not empty enough. The void is there, but its size and emptiness are not nearly sufficient to account for the full drop in temperature. The explanation almost works, but not quite. That has led some scientists to dream up more exotic possibilities. Perhaps they suggest the cold spot is not merely an internal quirk of our own universe, but the scar of something far grander. One particularly fascinating idea is that it may be the bruise of a collision, an ancient scar left behind when our universe bumped into another, during the brief period of cosmic inflation, when the universe expanded faster than the speed of light just after the Big Bang. If true, the cold spot might not only tell us about the early universe, but also hint that our universe is just one bubble in a far greater cosmic foam. Of course, no solid evidence yet supports this breathtaking theory. Still, it remains one of the most enticing possibilities because of the cold spot's precise alignment and the way it stubbornly appears in every set of observational data, no matter how carefully scientists check their instruments. There is also another twist. The cold spot is not alone. Astronomers have noticed that many other strange features of the CMB, not just this one, tend to show a preference for the southern sky. Odd alignments of large-scale temperature patterns, statistical imbalances between the northern and southern hemispheres, and unusual axes of evil, as some jokingly call them, all seem to point below the galactic plane. Some argue these are just artifacts of observation, perhaps slight errors in calibration or measurements. But repeated cross-checks with different satellites, different instruments, and different data filtering techniques continue to confirm that the anomalies are real. Even more intriguing, the area around the cold spot is one of the cleanest windows to the CMB in the entire sky. There is very little cosmic dust, very few interfering signals, and hardly any background noise. That means this patch of space is like a pristine laboratory, where cosmologists can test their theories about the beginning of the universe. It also means that any unusual finding in this region carries more weight, because there is nothing obvious to blame it on. Today, the cold spot remains one of the most puzzling discoveries in all of cosmology. It is not something you can see with your naked eye. It does not glow, shine, or sparkle. Instead, it is a subtle chill, a whisper in the ancient light, detectable only with the most sensitive instruments. Yet, despite its quiet nature, it echoes through every attempt to explain our cosmic origins. It lies not far beneath the plane of our solar system, haunting the great southern sky like a bruise on the fabric of reality. Some scientists see it as a statistical oddity, others as a cosmic desert, and still others as the possible fingerprint of another universe brushing against our own. Whatever it may be, the cold spot stands as a reminder that even in the vast and seemingly well-mapped sky, mysteries still lurk. Mysteries that may hold the key to understanding not just where we came from, but whether our universe is truly alone. Far beyond the stars that shine in our night sky, beyond the glowing galaxies we can see with telescopes, scientists have discovered something astonishing through powerful computer simulations. These simulations, which recreate the growth and evolution of the universe, suggest that hidden beneath everything visible is an enormous unseen skeleton. This skeleton is not made of bones, nor of any material we know. It is made of something mysterious called dark matter. Dark matter is unlike the normal matter that makes up our bodies, planets, and stars. We cannot see it, touch it, or hold it. Yet scientists believe it makes up most of the universe's mass. It is the invisible scaffolding that holds everything together. Without it, galaxies might never have formed, and the universe might look completely different. But dark matter is not spread out smoothly across space. Instead, it stretches and coils through the cosmos in a gigantic and tangled pattern called the cosmic web. This web is not delicate like the silk threads spun by a spider. Instead, it is built from colossal filaments of invisible mass that stretch for hundreds of millions of light years across space. These filaments weave through the universe like ghostly highways, connecting glowing knots of light where galaxies are born and gathered in enormous clusters. But the web is far from simple. It is rough and uneven. The filaments grow thick and rope-like around massive galaxy clusters, where gravity is strongest. In contrast, they become wispy and faint in the vast, empty regions of space, known as cosmic voids. Some of these filaments even split apart into smaller branches, reaching deep into individual galaxies like veins carrying unseen currents. Our own Milky Way galaxy is no exception to this invisible framework. To us, the Milky Way appears as a beautiful spiral of stars, gas, and dust. Yet it is wrapped inside a much larger ghostly cocoon of dark matter known as a halo. Within this hidden halo may run smaller strands of dark matter, tiny subfilaments, that could even pass through the region of space where our solar system drifts. These invisible threads may cross silently above and below the galactic disk without us ever noticing. But this raises a big question. If dark matter cannot be seen or touched, how do scientists know it exists? The answer lies in a strange and marvellous trick of nature called gravitational lensing. Normally, light travels in straight lines, but when light passes near a massive object, gravity bends its path, almost as if the object were a giant magnifying glass. Astronomers carefully measure how light from faraway galaxies is stretched, curved, or warped as it travels toward us. These tiny distortions allow them to create maps of the hidden mass in the universe. Time after time, these maps reveal the same pattern. Web-like threads of dark matter stretched across the sky, linking galaxy clusters together in a cosmic net. Some computer models go even further, suggesting that our solar system itself may occasionally pass near one of these dark matter strands. Inside the Milky Way's larger halo of dark matter float smaller, denser clumps called subhalos. If one of these invisible knots drifted close enough, it could slightly tug on the orbits of planets, stir the icy comets in the outer solar system, or even create faint lensing effects that might be detectable with highly precise instruments. So far, no scientist has directly observed one of these local filaments near us, but they are getting closer. The European Space Agency's Gaia mission, which is mapping the motions of more than 1 billion stars, is beginning to spot small wobbles and ripples in star streams. These tiny disturbances may be the fingerprints of dark matter, clumps gliding quietly through the galaxy. If a dark matter filament ever drifted near our solar system, we would not see it shine. Instead, we might notice its invisible presence only through its gentle tug on nearby stars and clouds of gas. Researchers are also beginning to wonder if these filaments of dark matter influence something else: the paths of cosmic rays. Cosmic rays are extremely fast, high-energy particles that race through space at nearly the speed of light. Denser strands of dark matter, with their gravity and perhaps their magnetic effects, might bend the trajectories of these particles or alter their energies ever so slightly. If this turns out to be true, studying cosmic rays could provide yet another way to map the hidden shapes of dark matter's threads. Should we be afraid of these invisible structures drifting through space? The answer is almost certainly no. Dark matter is unimaginably thin and diffuse. Even in the thickest parts of a filament, there may be only a few dark matter particles in a space as large as a household refrigerator. To us, that would feel like complete emptiness. Yet, on the grand scale of galaxies, the pull of dark matter is powerful enough to guide the dance of star clusters, bend the paths of stellar streams, and even steer giant clouds of gas so that new stars can be born. Over the course of millions of years, dark matter filaments may decide where galaxies grow, how comet clouds like the Oort cloud are stirred, and how spiral arms shift slowly through space. Looking toward the future, scientists are designing even more sensitive tools to search for the faint traces of dark matter. One of these projects is the Laser Interferometer Space Antenna, LISA, which will try to detect weak gravitational waves, tiny ripples in space itself, that might emerge if filaments of dark matter interact. Another ambitious mission, called CMB-S4, will study the faint afterglow of the Big Bang, known as the cosmic microwave background. By searching for tiny distortions in this ancient light, it may reveal the fingerprints of dark matter structures formed when the universe was still young. If all of these predictions prove true, then the night sky above us is hiding far more than stars. Flowing invisibly across the galaxy may be entire rivers of dark matter, moving silently, shaping the future of the Milky Way without ever shining a single ray of light. They are the hidden threads of a story still unfolding, the story of how the universe holds itself together. Rogue planets are perhaps the loneliest wanderers in the entire universe. Unlike the familiar planets that circle around stars, basking in their warmth and glowing skies, these strange worlds drift endlessly in the cold, dark spaces between the stars. They carry no sun to light their skies, no steady warmth to comfort them, and no day or night to mark the passing of time. They are like ships adrift in a sea without a lighthouse, sailing forever through a silent ocean of shadows. Some of these lonely travellers were not always so alone. Long ago they were faithful companions of stars, moving gracefully around them in steady orbits, just as Earth moves around the Sun. But the universe can be violent and unpredictable. Enormous gravitational struggles, cosmic tug-of-war battles between giant planets, or sudden encounters with passing stars sometimes fling a planet away from its home. Thrown out with incredible force, the planet is cast into exile, forever banished to wander the dark gulf between stars. Other rogue planets never knew the comfort of a star at all. Some were born in solitude, forming from clumps of gas and dust that collapsed in the darkness, never gathering enough heat or light to ignite a star of their own. These planets entered the universe as orphans from the very beginning, doomed to live without a sun to call their own. Most of these free-floating worlds travel within the wide, flat disk of our Milky Way galaxy, moving quietly among the billions of stars. But not all follow this ordinary path. Some come from unusual directions, falling in from above or below, arriving at sharp, unexpected angles. When a rogue planet approaches from galactic north, the region of space above the flat plane of the Milky Way, it comes from a direction that astronomers rarely study in detail. This makes it even harder to detect, as though it were sneaking into the galaxy from a hidden doorway. Finding these planets is no easy task. They're cold, dark, and nearly invisible against the black backdrop of space. But astronomers have found clever ways to track them. One of the most powerful tools is something called gravitational microlensing. This effect is a gift from nature itself. When a rogue planet drifts in front of a distant star, its gravity bends the light of that star. For a brief moment, the star appears to brighten and flicker, almost as if it were winking at us. That tiny temporary flash is enough to reveal the presence of an otherwise invisible world. Using this method, astronomers have discovered rogue planets both small and large. Some no bigger than Earth, others many times heavier than Jupiter, the giant of our solar system. The numbers are astonishing. Studies suggest that there may be billions upon billions of rogue planets drifting through the Milky Way. In fact, there may even be more of these lonely wanderers than there are stars. Imagine that for a moment. A galaxy not only filled with glowing suns, but also teeming with invisible, silent worlds hiding in the darkness between them. But how do some of these planets end up far above or far below the galactic disk? The Milky Way is not a flat, motionless sheet. It ripples and vibrates like the surface of a pond stirred by a breeze. It is constantly disturbed by enormous galactic events. When two galaxies collide or even pass near each other, their overwhelming gravity can hurl stars and planets out of their regular orbits. Some are flung so far that they end up in the galactic halo, a vast region of space high above or deep below the disk. Other rogue planets may have been ripped away from small dwarf galaxies or tight star clusters that once plunged through the Milky Way at odd angles, leaving trails of torn stars, drifting gas, and abandoned planets. In crowded star systems with 2 or more suns, chaotic gravitational pushes can also fling planets far out on long arcs, sending them soaring above the disk before they eventually fall back toward it. If a rogue planet were ever to approach our solar system from galactic north, it would be very difficult to notice. Most of our telescopes are designed to watch the galactic plane, or track the familiar paths of planets within our solar system. A dark, frozen world falling straight down from above would be like a shadow slipping into a room from the ceiling, while everyone is staring at the walls. Such planets give off almost no visible light. Without a parent star to heat them, they shine only faintly with the leftover warmth from their birth, a weak glow that can only be detected in infrared light. Powerful instruments such as the James Webb Space Telescope or the soon-to-be-launched Nancy Grace Roman Space Telescope are sensitive enough to catch that faint whisper of heat. But even for them, the search is like looking for a dying ember in an endless desert of night. Could one of these wandering planets ever come dangerously close to us? The chances are very small. Space is unimaginably vast, and our solar system is but a tiny speck in the galaxy. Yet, small does not mean impossible. Scientific models suggest that perhaps once every few million years, a rogue planet or similar object might pass within just a few light years of our Sun. Even without colliding with Earth or any other planet, such a visitor could cause disruption. Its gravity might disturb the Oort cloud, that enormous icy shell of comets surrounding the solar system, and send countless comets plunging inward. Like ripples spreading across a pond after a stone strikes its surface, waves of icy bodies could sweep into the inner solar system, some even heading toward Earth. Some scientists believe this might not be only a future possibility, but also something that happened in the past. A daring idea suggests that the mysterious Planet 9, the hypothetical giant world believed to exist far beyond Pluto, might not be a native planet at all. It could be a rogue planet that the Sun captured millions of years ago, pulling it into a long, stretched-out orbit that keeps it hidden in the distant dark. While this theory is still uncertain, it reminds us that our solar system's history may include encounters with visitors from the galaxy's untamed wilderness. The story of rogue planets also reveals something greater. They are like silent markers that help us trace the hidden structure of the Milky Way itself. By studying how these planets move, astronomers can refine their understanding of the galactic halo, the wobbling of the disk, and even the invisible influence of dark matter, the mysterious substance that acts as the skeleton of the universe. Though they are cold, dark, and silent, rogue planets may hold the keys to unlocking secrets about the very architecture of our galaxy. In the years ahead, new wide-field sky surveys will search for them more carefully than ever before. Missions such as the European Space Agency's Euclid Telescope and the Vera Rubin Observatory will sweep across the heavens, looking for the faintest flickers of these hidden wanderers, even those arriving from the overlooked regions of galactic north. The night sky may look full of shining stars, but the truth is that it could be just as full of invisible worlds. They drift unseen, like ghost ships in the ocean of the cosmos. And perhaps, even now, one of these silent travelers is slowly making its way toward us from the darkness above. There may be answers to some of the greatest mysteries of the universe hidden in a strange kind of matter that we cannot see. This invisible substance, known as dark matter, might carry secrets about the universe's very foundation. Some scientists believe that part of this mystery could be hidden beneath the flat plane of the Milky Way galaxy, in quiet and shadowy regions where even light itself seems hesitant to wander. To search for dark matter, researchers have gone to extraordinary lengths. They have built underground laboratories buried deep beneath mountains to shield their instruments from cosmic interference. They have placed telescopes high up in the thin air of mountaintops, closer to the heavens. They have even created powerful machines called particle accelerators, which smash atoms together at incredible speeds in the hope of revealing the hidden particles that may form dark matter. But there may be a different and less explored realm just below the organized plane of the Milky Way. In this mysterious layer, scientists suspect that unusual, invisible particles might be moving in great numbers. Among the leading suspects are WIMPs, short for weakly interacting massive particles, and axions, an entirely different kind of hypothetical particle. WIMPs are thought to be heavy, ghost-like particles that almost never interact with ordinary matter. They slip through planets, stars, and even our own bodies without leaving a trace, except for the faint tug of their gravity. Because of this, they are strong candidates for the main ingredient of dark matter. Axions, by contrast, are imagined to be feather-light particles. They were first proposed as a way to solve a puzzle in a branch of physics called quantum chromodynamics, which deals with the forces that hold atomic nuclei together. But axions might also explain the hidden mass of the universe. Unlike WIMPs, axions could behave in unusual ways. They might gather into vast wave-like fields or condensates, and they might interact faintly with magnetic fields, giving them very different properties inside galaxies. To understand where such particles might gather, imagine the Milky Way not only as a shining spiral of stars but also as a thick disk filled with swirling gas, dust and radiation. Most of the galaxy is restless. Exploding stars send shockwaves through space, newborn stars pour out fierce radiation, and the central bulge of the galaxy releases storms of energy. Yet just below the central flat layer, the galactic midplane, there exists a calmer region. It is not as disturbed by exploding stars or strong radiation. This quiet zone, at the uniform heart of the disk, may act like a gravitational basin where slow-moving cold particles naturally settle. Over time, it could gather thin but extended layers of dark matter, perhaps forming subtle structures just below the plane of the galaxy. Computer models of galaxies support this idea. They suggest that dark matter does not always form smooth halos around galaxies. Instead, it may clump together in smaller shapes and patterns. Some of these clumps, called streams or caustic rings, might drift through the galaxy in specific directions. If one of these invisible streams passes near our solar system, it could mean that a steady flow of dark matter particles is reaching Earth, sometimes from below, along upward paths that few instruments are currently designed to track. Detecting these elusive particles is an enormous challenge. That is why scientists have built experiments such as Xenon, Lux Zeppelin and ADMX. These machines are designed to catch the briefest and rarest events. A WIMP striking the nucleus of an atom deep underground, or an axion transforming into a faint photon of light inside a powerful magnetic field. But Earth itself complicates matters. As our planet spins and orbits the Sun, the angle at which dark matter particles arrive changes slightly. This means that detection rates rise and fall with direction and season. Researchers are now considering whether these changes might also be influenced by Earth's position relative to the galactic midplane, especially if some particles are streaming from below. Our solar system does not sit exactly in the middle of the Milky Way's disk. The Sun is currently about 20 light-years above the galactic midplane. Over time, it moves in a slow up and down rhythm through the disk, like a ship bobbing on cosmic waves. This oscillation takes about 60 million years to complete. Right now, we are slowly drifting downward, falling toward the galactic underlayer. This descent could be leading us into regions with higher or different concentrations of dark matter than we have ever encountered before. Some scientists think this vertical motion could explain puzzling results from certain experiments. For example, the Dama Libra detector has reported unusual seasonal patterns in its data, signals that might fit with the idea that Earth is passing through denser streams or sheets of dark matter beneath the galactic plane. In some models, axions may not just float randomly, but instead line up into great filaments or thin sheets. If these structures extend below the plane of the Milky Way, they could cross Earth's path at sharper angles than expected, creating bursts of detectable particles at specific times. Beyond the traditional detectors, a new generation of tools is on the horizon. Scientists are experimenting with quantum technologies, such as atom interferometers, devices that use the delicate motion of atoms to measure tiny disturbances, and superconducting microwave cavities, which may be able to sense axion-like particles with far greater precision. One bold idea is to point such instruments not only along the familiar path of the solar system's orbit, but downward, below the galactic disk, toward the quiet southern skies of the celestial hemisphere. By looking in that direction, we may be able to sense particles that have gone unnoticed until now. If these instruments succeed, they will not only reveal more about the nature of dark matter, They could also uncover the hidden architecture of our galaxy itself. Instead of imagining dark matter as a simple, smooth fog that fills space evenly, we may find that it is arranged like an invisible web of filaments and streams, threading its way beneath the stars. This unseen structure may shape the very way galaxies form, grow, and move through the cosmos. And humanity, perched on a small planet in the suburbs of the Milky Way, is only just beginning to peel back the curtain on this great cosmic mystery. When most people try to picture the universe, they often imagine something neat and orderly, a great flat disk where planets, moons, and comets quietly circle around the sun in smooth and steady paths. In this picture, everything sits nicely on a single plane, as if the cosmos itself were a tidy dinner table. The Earth's own path around the sun, which astronomers call the ecliptic, feels like the clearest example of this order. It is like a line of balance in space, a rule of symmetry that seems to keep everything in its proper place. But this is only the surface of the story. Beneath this thin skin of order lies something stranger, older, and far less studied. A hidden realm of chaos and mystery. It is a place where fragments of the past drift like forgotten relics, where comets plunge in unexpected directions, and where invisible rivers of gravity twist and pull in ways that defy our neat diagrams. In many ways, it is like an underworld of the solar system, dark, restless, and filled with secrets. The best-known citizens of this hidden domain are asteroids and comets. Most of them remain close to the ecliptic, circling along like faithful travellers on a highway. Yet not all follow this rule. Some, especially those that come from the faraway Oort cloud, dive steeply down from above or below. One of the most famous examples is Halley's Comet. Unlike the planets, which all move in the same general direction, Halley's Comet races along a tilted path, travelling backward compared to the planet's motion. Its orbit dips beneath the ecliptic, only to swing back upward again in a grand, dramatic arc. Other icy wanderers, such as the dark centaurs or the mysterious Damocloids, behave in much the same way. They slip in at odd angles, crossing beneath the ecliptic like shadows on hidden currents. Many long-period comets, which take thousands or even millions of years to complete their journeys, arrive on paths so steep and unpredictable that they seem almost random. When seen from the side, their travels look like sharp plunges from the southern depths of the solar system. They sweep past the sun in a flash of brilliance, then soar upward again, vanishing into the dark. Though their visits are brief, these comets hint at the enormous gravitational forces that shape the farthest outskirts of our system. Beyond the icy band known as the Kuiper Belt lies an even wilder territory, the scattered disk. This is a sprawling halo of frozen worlds and shattered fragments, many of which rest far below the ecliptic. Some scientists believe their strange alignments may not be accidental. They suggest that a hidden world, a giant planet sometimes called Planet 9, could be lurking out there. This world, still only a theory, might be tugging at these distant bodies, pulling them into steep orbits that dive beneath the ecliptic. If true, then what lies below our familiar solar plane may be influenced by the gravity of an unseen giant. But gravity alone does not tell the whole story. The sun and planets are not standing still in space. The entire solar system is moving like a great ship, sailing through the galaxy itself. As we drift along, we create a kind of gravitational wake, sometimes described as a bull wave, in the thin gas and dust of the interstellar medium. And our motion through the galaxy is not flat. It tilts slightly upward compared to the ecliptic. Because of this tilt, much of the material that drifts below the ecliptic may be more easily disturbed, swept inward, or tugged by galactic currents as we move through the wider Milky Way. There is also the hidden role of the sun's magnetism. The sun's magnetic field stretches outward in a great spiral, shaped by the rotation of the star. This structure is called the heliospheric current sheet. It is like a giant wavy blanket of charged particles twisting above and below the ecliptic. This current sheet reaches billions of kilometers into space, curling and folding beneath the ecliptic like a flowing curtain. Streams of solar particles and magnetic fields are dragged with it, creating a deep and shifting magnetic underworld. These invisible forces bend cosmic rays, scatter grains of dust, and trap drifting particles from interstellar space. spacecraft have given us rare glimpses into this hidden region. The Ulysses probe, launched in the early 1990s, was built mainly to study the Sun's polar regions. But as it moved out of the ecliptic, it also revealed how plasma flows and magnetic fields behave far from the solar plane. Voyager 2, which crossed just below the ecliptic as it left the heliosphere, recorded strange particle streams, sudden shock waves, and the southern edge of the Sun's influence. Its findings hinted that space below the solar system may not be a simple reflection of the space above. It may be shaped in a different way altogether. Closer to home, even some near-Earth asteroids carry hints of this hidden order. One striking example is the asteroid known as 3200 Phaethon. Its orbit is shaped like a long ellipse that cuts beneath the solar plane. Because most telescopes are aimed along the ecliptic, where the majority of objects are expected, many tilted bodies like Phaethon may still be hiding, slipping past our searches unnoticed. And then there is the faint zodiacal cloud, the hazy band of dust made from crumbling asteroids and the trails of comets. To the naked eye, it looks like a soft glow stretching along the ecliptic. But infrared telescopes such as ERAS and WISE have revealed that this cloud is not thin and flat. Instead, it has surprising depth, spreading above and below the solar plane. The dust beneath the ecliptic scatters sunlight and re-emits it as a faint warmth in infrared light, creating a ghostly glow that most people never see. These telescopes have mapped the hidden dust, showing how it drifts and dances under the combined pull of gravity, the push of solar wind, and the twists of magnetism. So what then lies beneath the ecliptic? Not emptiness, but an entire hidden landscape. It is a realm of tilted orbits and crooked paths, of wandering comets and strange fragments, of invisible magnetic waves and subtle galactic currents. It is not simply a mirror of what lies above, it is its own strange, restless world. Here, comets rise like ghosts from the darkness. Here, unseen planets may tug at the edges of reality. Here, the forces of the sun and the galaxy fold and stretch space into shapes we are only beginning to glimpse. Far below the flat middle layer of our galaxy, in regions where sunlight fades away and great clouds of gas vanish into emptiness, there may be some of the rarest and most mysterious things in the universe. These are called primordial black holes. Unlike ordinary black holes, which are born when giant stars explode and collapse, these ancient ones were never tied to stars at all. They are thought to have come directly from the chaos of the newborn universe. Primordial black holes, or PBHs for short, could be incredibly tiny compared to the monstrous black holes we usually imagine. Some may have been no larger than an asteroid, while others could have been as massive as a mountain. And yet, despite their small size, they are among the most intriguing candidates for dark matter, the invisible substance that makes up most of the universe. The mystery lies in the fact that they are only a theory. They do not glow, they do not reflect light, and they are almost impossible to detect. If they exist, they may be gliding quietly beneath the galactic disk, hidden in the cold and silent dark. Scientists believe that these black holes might have been created during the very first instant after the Big Bang, within the very first fraction of a second. At that time, the universe was a storm of violent fluctuations in density, and some of those fluctuations could have collapsed straight into black holes. Unlike the black holes we know from exploding stars, primordial ones could cover a huge range of sizes, from tinier than an atom to heavier than thousands of suns, depending on how big those early density spikes were. In a way, they are like fossils of the cosmos, relics from a time before stars, before planets, even before galaxies had formed. But why would scientists expect to find them beneath the galactic midplane? The answer lies in the quiet mechanics of the Milky Way. Dark matter, wandering stars, and even black holes do not just circle in neat, flat paths. They also bob up and down, rising above and dipping below the disk, tugged by the galaxy's gravity. The Sun itself follows such a path, gently moving up and down through the midplane about once every 60 million years. Tiny primordial black holes, if they exist, could be caught in similar vertical orbits. That means some of them could drift naturally into the hidden southern side of the galaxy, where clouds are thinner and fewer stars get in the way. These low-density regions are perfect hiding places. With fewer stars and fewer exploding remnants of supernovae, there is far less background noise. That makes it easier to notice the faint gravitational fingerprints of something as elusive as a primordial black hole. Even though they do not shine, they still bend light around them. Scientists use a technique called gravitational microlensing, watching for the moment when a black hole drifts in front of a distant star and briefly magnifies its light like a cosmic magnifying glass. Ongoing surveys such as OGLE and the future Vera C. Rubin Observatory are watching the sky for these small but telling blips. And the quiet southern fields beneath the galactic plane may be the very best laboratory for this hunt. But gravitational lensing is not the only clue. If a primordial black hole were ever to pass near our solar system, it would not just bend the light of distant stars. Its pull might leave tiny fingerprints on the orbits of asteroids, nudge a spacecraft off course, or even disturb the thin web of dark matter itself. Detecting such subtle effects would require the most precise models of the Sun's motion and of the orbits in our solar system, but these signs could reveal what our eyes cannot see. Another possible clue comes from gamma-ray signals. According to Stephen Hawking's theory, black holes can slowly evaporate by giving off faint radiation, a strange quantum effect now known as Hawking radiation. If primordial black holes are evaporating, they might be leaking out weak gamma-ray signals. The southern galactic hemisphere, which is quieter and less crowded than the northern side, offers an excellent window to look for such whispers of energy. Some scientists have even suggested that certain puzzling gravitational waves, ripples in space-time first detected by LIGO and Virgo, might have been caused by two primordial black holes colliding. If they tend to gather in low-density areas, then the dark underside of the galaxy may be a place where such collisions are more likely to happen. If so, the echoes of their mergers would travel across the universe as ghostly vibrations, the only evidence of events we cannot otherwise see. If primordial black holes make up even a small part of dark matter, then Earth itself may sometimes drift through streams of them as it journeys around the Milky Way. Right now, our planet is moving downward toward the southern side of the galaxy. That means we may be heading into a region where hidden gravitational shocks and strange disturbances wait for us in the dark. We may never capture a picture of a primordial black hole. They may always remain unseen, drifting in silence beneath the galactic floor. But even if invisible, their presence might still be felt, in the bending of starlight, in the slight wobble of an orbit, in the faint hum of space-time ripples echoing through the cosmos. Somewhere deep below, in the vast ocean of darkness under our galaxy, these ancient objects may still be floating as they have for billions upon billions of years, silent witnesses to the birth of the universe itself. High-energy cosmic rays often reach us from above, falling toward Earth like invisible arrows shot from the farthest edges of the universe. To the human eye, the night sky may seem peaceful, a place of steady stars and quiet planets gliding in their orbits. But in truth, outer space is not calm at all. It is more like an endless battlefield where unseen bullets are always flying in every direction. These bullets are what scientists call cosmic rays. Despite their name, cosmic rays are not beams of light in the usual sense. They are tiny particles, mostly protons, some heavier atomic fragments, and a smaller number of electrons that carry staggering amounts of energy. They rush through space at almost the very speed of the light, faster than anything we could ever build. Some cosmic rays are forged in the violent explosions of dying stars, in the roaring furnaces of supernovae. Others may come from even stranger places that we still do not fully understand, perhaps from the hearts of galaxies or from cosmic events more powerful than anything we can imagine. Many of them seem to rain down from above the solar system. Strangely, there is a heavier concentration coming from above the thin, flat plane where the planets circle the Sun, a region known as the ecliptic plane. Why this happens is still unsolved, but scientists think it has to do with the way our galaxy's magnetic fields twist and bend, with the Sun's own magnetic forces, and with the vast protective bubble that surrounds us called the heliosphere. The heliosphere is like an invisible shield stretching far beyond all the planets. It is formed by the solar wind, the constant stream of charged particles blowing outward from the Sun, and the Sun's powerful magnetic fields. This shield does not keep all cosmic rays out, but it changes the way they reach us. When these fast-moving particles approach from interstellar space, they collide with this solar wind and magnetic barrier. Sometimes the shield is strong and fewer rays get through, At other times, such as during the solar minimum, when the sun is quiet and its activity is at its lowest, the shield grows weaker and more cosmic rays flood into the inner solar system, especially from the sun's northern direction. We have even sent scouts to test this invisible frontier. Voyager 1 and Voyager 2, the famous spacecraft launched in the year 1977, have journeyed to the edge of the heliosphere. Voyager 1, which crossed the northern boundary of this bubble, recorded a sharp rise in the number of cosmic rays, a clear sign that it had stepped outside the sun's protective influence and into the raw stream of galactic radiation. The fact that so many rays seem to pour in from above may mean that our solar system is moving through a cosmic headwind, or that the galaxy's magnetic fields are shaped in such a way that they funnel radiation toward us. Here on Earth, scientists use all kinds of clever tools to track these mysterious messengers. Balloons released over the icy skies of Antarctica, as well as sensitive ground-based detectors, measure the cosmic rays that strike our atmosphere. They have found that the poles of Earth are hit harder than other places. This happens because both the Earth's and the Sun's magnetic fields guide the charged particles toward the poles. When they plunge into our atmosphere, they collide with atoms in the air and unleash dazzling light displays. The auroras, those glowing curtains of green, red, and violet that ripple across the skies near the Arctic and Antarctic. But among all cosmic rays, there is a special group that puzzles scientists the most: the ultra-high energy cosmic rays. These are the champions of the universe's particle world. They carry more energy than anything humans have ever created, even in Earth's most powerful machines like particle accelerators. In fact, some of these particles hold millions of times more energy than what we can generate. And yet, they simply fall toward Earth from the sky. Many seem to come from above the plane of the Milky Way, but their exact sources remain hidden. Some scientists suggest they might be born near supermassive black holes, in the violent centers of galaxies, or during titanic explosions called gamma-ray bursts. Others admit that we may be seeing something entirely new. To solve this cosmic mystery, massive projects have been built. The Pierre Auger Observatory in Argentina spreads across the land like a giant net to catch these rare particles. Meanwhile, above our heads, the Alpha Magnetic Spectrometer attached to the International Space Station maps cosmic rays with extraordinary precision. This instrument has even detected something especially strange: an excess of positrons, which are the antimatter twins of electrons streaming in from above the ecliptic plane. This finding has sparked bold ideas. Perhaps dark matter is annihilating itself nearby, releasing these particles, or perhaps hidden cosmic engines are at work just beyond what our telescopes can see. Cosmic rays are both wondrous and dangerous. They can slip straight through spacecraft walls, through the fragile electronics inside, and even through the bodies of astronauts. On Earth, our atmosphere and magnetic field keep us mostly safe, but in deep space, beyond this protective shield, the danger grows. For future voyages to the Moon, to Mars, or even farther, this invisible radiation poses one of the greatest challenges. Engineers are already working to design smarter spacecraft and stronger shields, using the patterns of incoming cosmic rays as guides. In the end, cosmic rays are like whispers of the universe, tiny, energetic messengers that carry stories of explosions, black holes, and perhaps even of hidden forces beyond our understanding. They remind us that space is not empty silence, but a living, restless storm of energy, always reaching for us across the great cosmic ocean. Physicists have spent decades chasing a ghost of an idea, a mysterious particle called the magnetic monopole. If such a thing were ever found, it would completely change how we understand electricity and magnetism. Normally, a magnet always has two ends, a north pole and a south pole, no matter how many times you cut it in half. A monopole, however, would be different. It would carry just one pole alone, either north or south, but not both. Scientists have never seen one directly, yet the possibility of monopoles is taken very seriously in the most advanced theories of physics. They appear naturally in grand unified theories, often shortened to guts, and also in some versions of string theory. These theories suggest that monopoles are not fantasy, but real things that may simply be very hard to find. So, where could we possibly look for them? One promising place is in the quieter regions of space below the path of our Sun, far away from dense matter and messy magnetic storms. Monopoles are thought to be extremely rare, perhaps created in the very first split seconds after the Big Bang, much like primordial black holes. If they do exist, they would not be tiny and light like electrons. Instead, they would be immense, possibly thousands of times heavier than a proton. Their great weight means they would not fly quickly through space like cosmic rays do. Rather, they would move slowly, drifting along the magnetic field lines of the galaxy, like beads sliding gently down invisible strings. Below the central plane of our Milky Way, space becomes calmer. The number of stars and the amount of glowing plasma drop sharply. There is less magnetic noise from exploding stars, radio bursts, and turbulent solar winds. In these quiet zones, the long, orderly magnetic fields of the galaxy are easier to pick out. If monopoles exist, they are most likely to follow those fields, and that is exactly where astronomers should be looking. Imagine the galaxy as a tangled bowl of magnetic spaghetti. The southern side of the galaxy may be one of the cleanest strands, and scientists are already watching. Powerful instruments like IceCube, buried deep in the Antarctic ice, and Antares, resting in the deep waters of the Mediterranean Sea, have both searched for signs of monopoles by looking for rare glowing tracks of energy left in water or ice. So far, nothing has turned up, but some physicists argue that the best chance lies not on Earth at all but out in space, especially beyond the reach of the Sun's magnetic field, where its constant turbulence no longer drowns out faint signals. A spacecraft stationed below the ecliptic, looking toward the galactic South Pole, could be perfectly placed to catch a slow-drifting monopole. Another clever method involves superconducting loops, rings of special material where electricity flows forever without resistance. If a monopole passed through such a loop, it would cause a permanent change in the current, almost like a toll gate counting a passing traveller. One day, fleets of robotic probes might carry these loops into the quieter southern reaches of the galaxy, scanning for strange disturbances in the magnetic silence. Some researchers even imagine that monopoles might sometimes be caught temporarily by the magnetic fields of planets, or trapped in Earth's long magnetic tail, only to be released during violent geomagnetic storms. But in the wide, dark stretches of interplanetary space, especially beneath our Sun's orbit, they would have the freedom to drift undisturbed, leaving subtle clues for us to find. For this reason, future deep space missions may carry finely tuned magnetometers designed to catch even the faintest trace of such a particle. Why does this matter so much? Because if magnetic monopoles exist, their discovery would confirm bold predictions that physicists have been making for half a century. Even more importantly, they could explain one of the deepest mysteries of the universe, why electric charge always comes in fixed, identical amounts. Every single electron in the universe carries exactly the same negative charge, as though nature stamped them all with the same mould. That odd consistency, as strange as it seems, could be the direct fingerprint of magnetic monopoles lurking somewhere in the cosmos. These particles are not just missing puzzle pieces, they may be the key to uniting all the forces of nature, gravity, electromagnetism, and the nuclear forces, into one grand picture. So far, no one has caught one. But in the cold, quiet, magnetically clean basement of the galaxy, far to the south of our familiar skies, the hunt continues. Somewhere in that hidden darkness, the secret may be waiting, the particle that could finally tie together the story of the universe. Neutral hydrogen is one of the universe's most widespread but least noticed ingredients. Imagine it as a vast, invisible ocean lying beneath the main disk of our galaxy, the Milky Way. Unlike the shining brilliance of stars or the roaring energy of quasars, neutral hydrogen does not glow or dazzle. Instead, it hums faintly at a special frequency of 1,420 MHz, a cosmic whisper rather than a shout. This neutral hydrogen, often called HI, is just the simplest kind of atom, one lonely proton paired with one equally lonely electron. By itself, a single atom is impossible to detect, far too faint to notice. But when billions upon billions of them gather into great clouds, they give off radio waves at a very particular wavelength, known as the 21 centimeter line. This signal has become one of astronomy's most powerful tools, allowing scientists to trace out hidden shapes and movements of gas across the galaxy, even in regions where ordinary telescopes cannot see. The most fascinating discoveries are made below the galactic midplane, a quieter and darker zone where conditions are colder calmer, and more pristine than the crowded regions above. Radio surveys, such as those from the Hi4PI and Galpha High projects, reveal that hydrogen here is not spread evenly. Instead, enormous layered clouds stretch for thousands of light years, often curling and twisting into wave-like patterns. These clouds are not still, they drift and ripple, pulled and sculpted by the galaxy's rotation and the tug of its gravity. Some of these gas structures form part of what astronomers call the galactic warp. Think of the Milky Way's disk as a giant spinning record that is not perfectly flat but bent, dipping downward on one side and arching upward on the other. Our own solar system is currently sliding downward into this bend, heading directly toward one of the densest regions of hydrogen in the southern sky. Why does this matter? Because neutral hydrogen is the raw fuel from which stars are born. Long before a star shines, it begins as a cold, dense cloud of hydrogen slowly collapsing under gravity. By studying these hidden layers of gas beneath the galactic disk, astronomers are essentially watching a time-lapse of stellar history, especially in quiet, low metallicity regions where ancient processes still echo. These gas clouds are like a memory of the galaxy itself, recording past events the way scars record old wounds. Indeed, some of the hydrogen streams found below the disk are relics of galactic collisions. Wisps of gas, perhaps once part of small galaxies such as the Sagittarius Dwarf or the Magellanic System, were pulled apart by the Milky Way's gravity and dragged down over billions of years. These streams continue to move on their own, colliding with the halo of gas around the galaxy and creating shock waves, compression zones, and changes in temperature that can either spark the birth of new stars or smother it entirely. Among the most puzzling mysteries are the so-called high-velocity clouds. These are enormous blobs of neutral hydrogen racing through space at speeds that do not fit the normal rotation of the Milky Way. Many of them lie below the galactic plane, and their origin is still uncertain. Are they leftovers from ancient collisions? Are they material blown out by long-gone stellar explosions now falling back into the disk? Or could they even be fresh gas arriving from the cosmic web itself, drifting slowly into the galaxy like cosmic rainfall? One of the most striking examples is the Smith Cloud, a colossal object of neutral hydrogen on a direct course toward the Milky Way, approaching from below the disk. This cloud carries enough raw material to form 1 million new stars and is rushing forward at nearly 240 kilometers per second. In perhaps 40 million years, when it slams into the Milky Way's disk, it could ignite a spectacular burst of star formation in the southern galactic hemisphere. Even before this dramatic collision, however, the shock waves it sends through the hydrogen layers beneath us may give astronomers priceless clues about how gas behaves in the deep, cold stretches of space. And this is only the beginning. With new technology, especially the square-kilometre array, an immense radio telescope soon to rise, astronomers will be able to chart these hydrogen layers in exquisite three-dimensional detail. They will track their movements, measure their density, and study how they interact with cosmic rays and magnetic fields. It will be a little like scanning the floor of a cosmic ocean, finding its sediment layers, its buried rivers, its fossil records of past events. So, while we often lift our eyes to the brilliant stars and glowing nebulae above, there is also a hidden world below, a quiet realm filled with ghostly hydrogen fog. It whispers across the radio spectrum, carrying stories of creation, collision, and rebirth. Neutral hydrogen is not just a background presence. It is the very foundation of galaxies, the seedbed of stars, and the silent witness to everything that has ever drifted into the Milky Way. Even though space often feels empty and calm, it is far from still. High-energy particles, cosmic rays, neutrinos, and ions, move through the galaxy in all directions, but not always evenly. This unevenness in particle flow is called directional anisotropy. Scientists have detected a mysterious cosmic whisper. Particles sometimes arrive from preferred directions rather than uniformly. Surprisingly, some of this flow seems to come from beneath the circular plane of the Sun, the vast invisible disk in which our solar system orbits. The term anisotropy simply means unevenness, and in this case, it describes how particles do not arrive the same from every direction. Sensitive instruments like the IceCube Neutrino Observatory in Antarctica, as well as cosmic ray detectors aboard satellites such as Pamela and MS-02, have consistently recorded small excesses and deficits in incoming particles depending on the region of the sky being observed. When the data is mapped across the whole sky, a remarkable pattern emerges. Some of the highest energy particles appear to be arriving from southern galactic latitudes, beneath the plane. This bias is not random noise. Statistically, it is significant, and in some cases it has remained consistent over many years of observations. This strongly suggests that the effect is a real feature of our nearby galaxy, rather than a measurement error or a quirk caused by Earth's magnetic field. But why would the particle flow favour one direction? One possibility involves galactic magnetic fields. Cosmic rays, especially lower energy ones, are influenced by these fields. If the southern galactic hemisphere contains denser magnetic lines, remnants of ancient supernova shockwaves, or coherent plasma structures, these could funnel or deflect particles upward toward the solar system. Picture this as an invisible cosmic subway system, moving near the speed of light, carrying particles along preferred routes. Another explanation might lie in the Milky Way's history of collisions. Over billions of years, our galaxy has absorbed smaller galaxies, leaving behind streams of stars, gas, and dark matter below the galactic plane. If these remnants include active black holes, collapsed cores, or dense clumps of dark matter, they could act as powerful particle accelerators, flinging high-energy particles toward us and producing the observed anisotropy. Our own motion through the galaxy also plays a role. The solar system is currently moving downward through the galactic plane, toward the southern sky. This motion creates a kind of kinetic frame shift, making incoming particles from below appear slightly more energetic, much like driving into a rainstorm makes the raindrops seem harder from the front. This effect, known as Compton-Getting anisotropy, magnifies directional differences and helps scientists separate real particle flows from observational biases. By combining measurements from instruments in both hemispheres over long periods, researchers have begun constructing three-dimensional maps of particle flows around the solar system. These maps reveal that the space beneath our feet is far more active than once believed. Even more intriguing, these particle anisotropies seem to align with other signals, such as gamma-ray gradients detected by the Fermi Gamma-ray Space Telescope and neutrino bursts recorded by IceCube. Many high-energy phenomena appear more frequent or intense in the southern sky beneath the plane. Are these coincidences, or clues to hidden sources, active remnants, magnetic funnels, or unknown astrophysical structures lurking below? Understanding these directional flows is not just academic. It improves models of space weather, which is crucial for future deep space missions. It may also reveal the distribution of matter and energy in hard-to-observe regions of the galaxy, and perhaps even hint at exotic physics, from dark matter decay to unknown cosmic accelerators. While most telescopes focus on the sky above, the space below is sending particles with stories to tell. Stories of movement, structure, and unseen forces. For most people, tides are the rise and fall of Earth's oceans caused by the moon, or the stretching of stars near black holes. But gravity stretches space over enormous distances, affecting stars, clouds, and even entire galactic disks. In the southern parts of the Milky Way, below the solar system, tidal forces from massive structures are subtly reshaping how stars move, how the solar system drifts, and possibly even the galaxy's overall shape. The Milky Way is not a static, flat disk. It ripples and responds to gravitational nudges from within and beyond. One major influence comes from the Sagittarius Dwarf spheroidal galaxy, a small satellite currently being devoured by our galaxy. Its tilted elliptical orbit plunges through the Milky Way's disk, sending ripples like stones dropped into a pond. These disturbances are strongest beneath the galactic plane, where Sagittarius leaves behind streams of stars, gas, and dark matter. Its gravity stretches the lower half of the Milky Way, tugging on stars, including our Sun, and even affecting dark matter distribution. Other satellites, like the Large and Small Magellanic Clouds, orbit below the southern disk. Their combined gravity drags dark matter and bends the Milky Way's outer ring, creating a gravitational wake. This uneven pull causes vertical waves through the stars and gas, a motion sometimes called galactic seismology. Recent data from the Gaia satellite, which maps the positions and motions of over 1 billion stars, confirms that these vertical waves rise and fall over thousands of light years, proving the disk is vibrating in response to ancient tidal impacts from below. These tidal forces may even influence life on Earth. Some researchers suggest that as the solar system moves up and down through the galactic plane, a cycle taking roughly 60 to 70 million years, it passes through denser regions of cosmic dust or experiences increased comet activity. This could coincide with mass extinction events, hinting at a subtle but real link between galactic tides and terrestrial history. The southern part of the Milky Way, pulled and warped by tidal forces, bends differently than the northern half. These forces do more than distort the disk. They reshape the galaxy, cluster dark matter, ripple gas clouds, and shift stars. Even the solar system is caught in this dance. Far from being empty, the vertical frontier below the galactic plane is full of invisible forces, unseen structures, and possibly the next great discoveries in astrophysics.